we are going to cover the regression part, right? So to understand the regression, we had started with a data. Okay, a data that I took is having what? 3 components like TV, radio, newspaper, and sales. The 4 components are there. So first I read the data over here, right? This column is not important column, so I can make that column as an index column. Okay, which column? You can see the unnamed 0. Okay, we can make it as an index column. So I'll use index underscore call is equals to 0. All right, now it's better. Okay, so here, why should we go with the regression? We should go with the regression because we need to build a model which can predict sales. Okay, we need to do what? We need to over here build a model. Okay, build a predictive model which can predict sales values. All right, so how can we start? Okay, so the very first thing we need to see, like, how can I predict the sales? So to predict the sales, I need some information. So I'll look at the data. I have information like TV advertisement cost, radio advertisement cost, and newspaper advertisement cost. Okay, these are the informations given. So these guys are called as what? Independent variables. Okay, and this is what? Dependent variable. Understood? This is also called features. Okay, and this is called what? Label. Okay, so we need to find out the best possible relationship between the feature and label. Okay, so here comes simple linear regression. Okay, multiple linear regression. Okay, regression, or you can say non-linear regression, right? Or later on Lasso, so many things are there. So question is, which one to use? So first you should know what they are, then only you can decide which one to use, right? So simple linear regression is something which uses one feature and one label. That's it. That means I have 3 features given, but I have to use only one feature. That is called simple linear regression. Okay, that means if I want over here to, like, suppose I consider X is my feature. So I say DF of TV. Only one feature over here. Y, this is what? DF of sales. Only one target. So when I try to build a best possible relationship, okay, between just one feature and one label, that is called what? Simple linear regression. Okay, what I mean? It means that suppose we have coordinate, X coordinate, I am representing with what? TV advertisement cost. Okay, and Y coordinate, we are representing what? Sales value. Okay, and then we have some informations given over here like this. Okay, like this, right? Like this. Okay, so what simple linear regression does? Simple linear regression will try to identify or try to figure out best possible linear relationship between these two entities. Okay, best possible what? Linear relationship between what? Between X and Y. Right, that is the purpose of simple linear regression. Okay, so now the question is how it can find out the best possible linear relationship. See, to do this thing, we have 2 different ways. Okay, the first way is called what? Ordinary least square. Okay, and second way is called what? Through error optimization, which is called gradient descent. Okay, so this is good at basic level, but most of the algorithm uses what? Gradient descent process, because every time you don't have to work with a single feature. Okay, you may have to work with a 2, 3, 5, 10 features, right? Okay, so let's say if I want to use over here ordinary least square. What is ordinary least square? Okay, to understand this thing, what I do, I'll just explain over here. Ordinary least square for simple linear regression. Okay, you make it into a comment. Actually, I was doing something else. Okay, so what is ordinal? So let's say I have a data, okay, like this. I'll define over here. Let's say x is equals to np dot array. Okay, let's say 3 comma 5 comma 9 comma 7 comma 10. Okay, something like this. Okay, and y is equals to what? np dot array. Okay, 4 comma 8 comma, let's say 9 comma 6 comma 9. Okay, something like this, right? Now I'll do what? I'll plot it. Import matplotlib dot pyplot as plt. So this is what? Plt dot scatter x comma y plt dot so. Okay, so now here, suppose using the x I want to predict y, right? So I have two options. Either I should find out some kind of equation which can represent, some kind of equation which can generate a line. Okay, I need to find out a equation which can generate a line which is passing through all the dots over here. But that is a discussion that we'll do in the non-linearity. Here we are discussing linearity. So I need to find out best linear relationship. That means I want to find out a line that is passing through this data. This line can have an equation like this. Okay, linear line is having equation like this. And when it will be called as a best possible line, if it will be at a minimum distance from all the given points. Okay, if this is minimum compared to all possible, like, because within this coordinates there are n number of lines possible, right? N number of linear lines possible. There is no limitation, infinite number of linear line possible, right? But out of all the possibility, what we required that particular line which can give me the least possible distance from all the given points, isn't it? That would be considered as what? Best fit linear line, isn't it? So what I want the equation of this line. Okay, if this is a equation of linear line, so I want the values of these guys. This is called what? Intercept. Okay, and this is called what? Coefficient. These two entity I want. X is already given to us, right? So to find out, we can make use of ordinary least square. What is ordinary least square? Let's check. Here we have a mathematical formula to do the things. Okay, so let's say, where is the formula? Here is the formula. Okay, so using this formula, we can find out first the slope of the line, and once we have the slope of the line, we can find out the intercept. Okay, this is being created. This equation is being given for y is equal to mx plus c. Okay, to find the m, this one we can use, and then with the help of m, we can find out the value of c, or it is b like this. Okay, we are going to use w0 plus w1x. Why I am using w0? Because in machine learning, deep learning, we consider weights. Okay, we consider these things as a weights, right? Like if this value is higher, that means my algorithm had given the higher weightage to this particular feature. Okay, if any feature is of higher weightage, of more importance, their coefficient will become higher, isn't it? So now let's try to implement this thing quickly and see how it will give us the result, right? So what I do, I'll find out over here x minus x dot mean. Okay, and thereafter we'll take the product of this guy with y minus y dot mean. Okay, then I can take the sum of it. Okay, then I can define it as a numerator, right? And what is denominator? Denominator can be according to the formula. It is x minus x mean whole square. Okay, this is the formula we have. Okay, and then we have to take the sum of it, right? So just take the sum of it quickly. Okay, and then when we divide it by, when we just divide numerator and denominator, what we get? We'll get the coefficient of x. So this will be n1 by d1. Print w1. Okay. Now with the help of it, I can calculate the w naught. That is your, if this is our equation, y is equal to w naught plus w1 x. All right. So now we can easily calculate w naught. This will be equals to what? Your y mean, right? So y dot mean, right? Because if we have a linear line, right, and we know that linear line is having an equation y is equals to mx plus c. Okay, so this linear line will have some point which is called y mean. Okay, this linear line will also support the equation for y mean, right? That's why we are using it over here, y mean minus w1 into x dot mean. Okay, so now I will have w naught.
Well, I did not understand why you are using y mean here. Sorry.
I'll explain. Okay. See, if we have this thing like this, right, and then we are trying to find out a best fit line. So using the least square method, we got the slope of this line. Okay, this is called slope. Okay, the slope of this line we got, right? Now once we have a slope of this line, we require this point. Okay, this is called what? Intercept. This is called what? Intercept, right? Y hat is equals to w naught plus w1 x. Okay, it means the value of y if x is 0, right? That means the value of y when features is 0, the feature
Got it.
is having 0 value.
Got it.
So I want this point, right? So now according to this equation, it can be like, if I want it, so I can y hat minus
W1.
like this.
Got it. Got it.
Right? So this equation, is representing a linear line. So in this line, whatever the points we have, this equation will satisfy all the points. That means the y average will also be somewhere on this line, right? So that means this equation will also support for y average and x average, right? So we are just considering that y average will be somewhere on this line, x average will also be somewhere in this line. So using these things, I can calculate this guy only from this equation. All right,
Makes sense.
okay. So now whether this is, now I want to check like how it is giving me any best fit line or not. So
Sir, WO is the intercept or it's the slope? I think it's slope, right?
W naught is the intercept.
Okay, the intercept, the starting point. Where,
Right.
right.
It is an intercept. That means the value of y when x is 0. Okay, so it would be like this. Let me just plot it. It will be more clear. Now, based on this thing, I had been given y. Now I will have y hat. The relation between y hat and your x, okay, is what? Linear. So now we calculated it. And based upon this linear relationship, if I'll try to plot it, let's try to plot once again. PLT dot plot x comma yh. Okay, and I can give it a red color line. Okay, so it means what? It means that this is a best fit line on this particular data. That means now if I know the value of x, okay, I can use this linear line to predict the value of y. Okay, so because whatever, like this line is what? Y hat is equals to, what is the value of w naught? W naught value is, just a minute. Okay, fine. So here, okay, so we got the equation over here, right? So using this line, right, I can easily predict the value of y. Okay, I have an equation y hat is equal to w naught plus w1 x. What is the value of w naught? 3.012 plus 0.616 into x. This line, if you extend over here, this is 3.012. Okay, this should be 3.02, right? But it is more than 4, it is showing, right? Is it correct? Something is incorrect or what? This thing will show me, just a minute, let me check once. Y w naught y1y is equal to mx plus 0. Something must be incorrect over here, I guess. What is incorrect? Just a minute. Here we have x and y defined, all right. Here I have x minus x dot mean, y minus y dot mean, dot sum. This is correct. X minus x dot mean, y minus y dot mean. This is correct, right? And then x minus x dot mean whole square dot sum. This is also correct. Denominator. Y mean minus w1 into x dot mean. Okay. 3.012 is a value, right? So it should go to 3.012 when the x value is 0. 3, 4. I guess here x value is not 0. Okay, that's the reason. Okay, I understood why it is like this. See here, this is not x0, isn't it? Because it is 3, so x0 may be somewhere little 3, 4, right? So it may be 2. Here it is 1, right? So x0 is little ahead, right? What I can do here, I'll tell you. I can explain it. First, what I do, I can use over here plt dot x limit. Okay, 0, 10. Okay, so now it is 0, 10. All right, so 0, let's say 12. Okay, so now now if you extend it, that's why I was also got confused. Now it's fine. Okay, now if you extend this guy,
So what is this x limit 0 to 12? I mean, you change the bar this thing, but why?
I'll tell you. This x limit. Yeah, I'll explain. See, now when you have the actual data, right? Let me just compare with the actual data. So when I have actual data, the actual data x value is what? Minimum it is 3, right? And maximum it is 10, right? So when I try to plot it, I not use x limit, right? So on the x-axis, it will start from 3 and set 10. All right. So that's why when I'm trying to plot this best fit line, okay, so it seems like it will cross the y coordinate at something 4.5, isn't it? But actually it should cross where? It should cross at 3.01, isn't it? Okay, so it was creating a little confusion, right? So we can avoid such confusion. PLT dot X limit as 0, let's say 12, and PLT dot Y limit is 0, 12. Okay. Now if I'll execute it like this, now what happened? If you see here, I'll extend this line. Just a minute. Okay. So now it is crossing at what? 3.012 whatever. Okay. That means our equation was saying that y hat is equal to 0.31. Sorry. What was the this one? What was the intercept? Intercept was 3.12 something plus 0. Whatever the coefficient. Are you getting it now? Okay. Let me just try once again. It may be a little confusing, but you'll get it. See, when we applied the ordinary least square, what we got? We got two entity of our best fit line. Okay. The first entity over here is what? Is slope. Okay. Slope of our equation. This is equation of what? Linear line. This is equation of linear line, isn't it? So the first entity that we got over here is what? Is slope of that linear line, 0.616. 0.6158 is there, so I'm using 0.616. Right. The second entity is what? That is intercept, 3.012. Right. That means when the value of x is 0, the value of y will be 3.012. So how can you verify it? To verify it, you can extend this line. Okay. If you extend this linear line, you will find it where it is intersecting when the value of x is 0. When the value of x is 0, where it is actually intersecting. See. It is intersecting at 3.012, right? Right? And the slope of this line will be represented by this guy. That means if you know the value of x, okay, if you know the value of x, what can you do? You can use this equation. Okay, if you know the value of x, you can easily use these equations to predict the value of y. Right? Like for example, let's say if I know the value of x, so I will use it. Okay, like suppose the value of x is 4.5. Okay, so I know 3.012 plus 0.616 multiplied by 4.5. I can easily predict the value of y. Am I clear?
Yes, people, but why didn't the earlier one work? Like, why did you have to set the limit? That is something I didn't understand.
So it is because your y coordinate values, the minimum y coordinate. Okay, fine. To understand this thing, let's remove it and try it once again and removing this limit. Okay. So now here your y is starting from 4. Why it is starting from 4? Because in the data 4 was minimum. Okay. And x was started from 3, right? So that means here if I am just suppose I am extending it over here. So here the value of x is not 0. Okay. When the value of x is equal to 0, then only y is equals to 3.012, right? So here y is not 0.12 because here y is what? Something looking close to 4.5, right?
Right.
Isn't it? Because x is not 0. X, here you can see 3. Okay, so 2 must be somewhere over here. You can see the difference, right?
Right.
Thereafter 1 must be somewhere over here and 0 is before that.
Okay,
right?
got it.
Right, so that's why it is intersecting over here and it is creating a confusion that our intercept is incorrect or something like that.
Makes sense. All right, thank you.
I think what you did was you made both the scales equal, 0 to 12, so that there is no like one is 0 to 4 or one is 0 to 6. So 0 to 12 equal in the scale, that will give us a better result, correct?
Right, just for the visuals, like less confusing. Yeah, less confusing visual, I did it.
Yeah, that's better.
Okay,
0 to
so
12.
that we can check over here that when, because at this point on this particular line all the x values are 0, right? So that's why when I extend it, I will find out it is intersecting exactly at the intercept. All right. Okay, so this is how we generally find out the best fit line. Okay, what we did, we have over here, that means using this best fit line, now I can, like, suppose I have a value of x, x underscore new is equals to 3.8. So to predict the y value of y, we can do what, y new is equals to w naught plus w1 into x underscore new, print y. Now what happened? This is the predicted value, but regression can't give you the exact prediction. Regression will always be used to predict the close value. Okay, very close. Okay, to the actual event, like when actually something, because suppose you have to predict the stock price. How can you predict exact stock price? Not possible. If you have to predict the sales value, you can't predict the exact sales value for tomorrow. You can predict what, close. Okay, whatever the process you use, you can just go as close as possible. Okay, like suppose you are predicting 3.456. Okay, in reality it may be 3.55, it may be 3.9, it may be 4, it may be 3. Okay, so we try to be close, right? So that's why here we do what, we calculate the error. Okay, so how can we calculate the error? We can calculate the error by calculating the difference between this YH, that is our predicted value using the identified coefficient and intercept, using the calculated intercept and coefficient. Okay, this is a coefficient, this intercept. So we calculated YH for all the given value of x. So it is, we can say what, calculated output on given x using linear equation components. Okay, using the linear equation components. All right, now using this, what I do, y minus YH. Okay, so this is what we will take over here. Now if I will print it, so I get what, error value is somewhere negative positive. I want to calculate the average, so I take the absolute value of it. Okay, now I can take the average of it. So this is what mean absolute error. Okay, this mean absolute error actually represents how good your model is. Okay, if it is lesser, your model is good. If it is not lesser, your model is not good. All right. So this is one of the way through which we can let a system understand between the given features and the labels, so that my algorithm can find out the best possible coefficient intercept, using which later on prediction can easily be made. Okay, the next step over here, that means the next way, this is what, just a, you can say, type 1 to find out. Okay, next I'll tell you about type 2. Okay, which this is going to be really important, which is gradient descent error optimization process. Okay, so I'll share this file right now with you. Okay. Before going ahead for the next explanation, I want you to go through this thing, okay, and figure out and let me know if there is any questions over here. And then we'll move to the next topic. Please have a look. The next topic I am going to explain is going to be very important. All right. Okay. You can access the file. Can you access the file?
Yes.
All right. Okay. So see, next is what? Let's say what we did here. We use the predefined formula. Okay. Good for simple linear regression. Okay, but may not work that good if you're going with a multiple linear regression or the equation becomes very complicated to solve and all, right? But there is a process that we use in machine learning that is called error optimization, which can be used in any kind of algorithm. Okay, this is very popular process, and in neural network, in deep learning, and in kind of advanced algorithm, right? Like logistic regression and all, this gradient descent is highly used. Okay, so what it does, it is used for error optimization. Error optimization means what? First we have to calculate the error. Okay, what do I mean? It is like this. Let's say I have the data given over here. Okay, and I want a best fit line. Okay, as I want a best fit line, so we know I that it should be a linear line. So as it should be a linear line, so this will have a equation like this. Okay, that means this equation requires two important entity, these two guys. We already have this one, but we don't have these two guys. So what we do, we first say that let's assume, okay, let's assume the value of w naught is equals to anything. Let it be 1, 2, 3, whatever. Okay, let it be 1. Okay, like this. Let's assume it like this. Right. Now, based upon these value, calculate your YH, W naught plus W1 into X. Okay. So now this is your YH. Okay. So based on the YH, calculate your error. So Y minus YH. Okay. So error will be combination of negative and positive. So what we can do, we have to convert them positive. So two options are there, absolute or square. We will take the square so that we can optimize it faster, isn't it? That means we are penalizing the error more. Okay, you can also take absolute, but if I take absolute, the way the error optimization will be slower. So just take the square, we penalize it more. Okay, so that if I will reduce the squared of error, actual error will reduce at much faster pace. Okay, and then I take the average of it. Okay, so it is what? It is our first error value. Okay, it is sorry. It is a first error value, and if I can optimize this error, if I have a process which can optimize this error, automatically the coefficients will also get identified. The best coefficient will get identified. So what I can do? Let's check. Okay, so here we have y is equals to w naught plus w1x. We calculated the error as y minus y hat. Okay. This we did at y minus w naught minus w1x. Okay. Now I want to tell you one important thing. If I write like this, y is equal to x square. Okay. This equation is represented like this. A curve. Okay. Y is equal to x square is what? Is basically a curve. Y x. Okay. This is a representation of this equation. So same thing we have over here. Here it is E. Okay. And on x-axis we can consider it as a x square kind of. This is also x square, right? That means something is square. That means the relation between this entity and this entity will be what? Will be a curve. Okay. That means there must be a point where error is minimum. Okay. So what is that point? Okay. You know, this y is constant, right? This y will not change. It is coming with the data. This is actual target value. Okay. This is actual target value coming with the data. X is also coming with the data, right? What are we changing? We are changing these two entities. Okay. We are changing either coefficient or intercept. That means we have to find out the coefficient and intercept where your E is minimum. That means this particular line, okay, will represent what? Weights. Will just represent what? Weights. Okay, here I can't pay. This X is what? X is coming with the data, so X we are not changing much. Anyway, we will not change. Y will not change. So error value will change, either increase or decrease, whatever, based on change of what? Weights. Right? So there is a weight for which error is minimum. So I have to find out that particular weight. So question is, how can we find out? Right? So to find out this thing, we'll do over here what? Partial differentiation of error with respect to weight. So this will be equals to what? 2y minus w naught minus w1x. Okay. So with respect to w naught, if I am partially differentiating, this 2 will come over here. This will remain as it is. And what is a constant with w naught? Minus 1. So this will be equals to what? Minus 2 y minus y hat. Now, if you forget differentiation and all, nothing to worry. Please don't worry. This is just basic understanding required. Most of the activity will be done by libraries. Okay, we are not going to do it manually. Just for understanding, I am telling you, isn't it? Next, we will also differentiate. This will be equals to what? Again, 2 y minus w naught minus w1x multiplied by what? Minus of x, because x is a constant over here. So minus 2 y minus y hat into x. Right. These two entities are called what? These are called gradient. Okay. Now, this will also represent a very small change in error with respect to a very small change in weights. Okay. That means E2 minus E1 upon W2 minus W1. Okay. What is this? Slope of a line. Okay. If you have any line like this. Okay. And here I have x2 and y2. Okay. And here I have x1 and y1. Right. The slope of this line is represented like this. Okay. This is a slope of any line. y2 x2 minus x1 upon y2 minus y1. All right. So same thing we are doing over here.
And sir, what is the green and blue one? A small change in error with respect to small change in weight. So one of your voice one and minus x.
Can you be little louder? I missed your voice, Leo.
M is the slope. I understand. I'm saying you're saying the a small change in error upon small change in weight. So the above
Correct,
equation says minus 1 and the another equation is minus x. I didn't get that. The last part. Minus m and sorry, minus 1 and minus x.
Yeah. See, if you have y minus y hat whole square, you replace y hat with the actual equation of y hat, right?
Right.
Okay. So it is minus. So minus will do what? Minus will make this thing also minus, right?
Smaller.
Alright. See, here this will be written as y minus w naught plus w1 x whole square, right?
Yeah.
Sorry. I should write it. Just a minute. Let me just clear it, then I'll explain.
So we will write the a square plus b square plus 2ab, or in differentiation we take the power of 2 to 1, just like log. In log,
Just
take that.
no need to complicate it. It's very simple. See here, you can write it like this: y minus this y hat w naught plus w1 x, okay, and then whole square.
Yeah.
Right. So when this thing will come out of the bracket, it will become what? Y minus w naught minus w1 x, right?
Right.
Isn't it? So from here minus came. That means if you differentiate it, so 2 will come over here. This whole equation will remain as it is. And then the coefficient of w naught. What is the coefficient of w naught? Minus 1, right?
Coefficient of w.
Here we have minus 1, right?
Yeah, for 1, yeah, right. One.
Yeah.
One.
And what is the coefficient of w1? Minus x, right? Minus
Yeah,
sign and x is there. So that's why minus x.
Okay.
Understood?
Right. Okay.
Okay.
So can't we open up the whole equation, a square plus b square minus 2?
No need. That is, it is not a plus b square kind of thing. It is different. Okay. Here we are differentiating. No need to open it up.
Okay. So
Okay,
when you're
we have to differentiate it.
when you're differentiating, the power which is there goes to the first, just like log. When you're saying 1 times.
Correct.
Yeah, that is what I was asking. So the 2
Correct.
will, if it was 3, then bracket all this things.
Correct. Okay. So as we are differentiating with respect to w naught, so this will be considered as a constant, right? This is already constant. This will also be considered as constant. Okay. So here I am trying to differentiating this one, change in error with respect to w naught. So only the w naught constant will be separated over here. When I am differentiating with respect to w1, only w1 constant will be separated over here. All right.
Right.
Okay. So it is called what? This is called gradient. These two entities that is calculated is gradient. Okay. And what gradient represents? Let's come back to your this curve. Suppose this is my first weight value. It is my what? First weight value. Because of this weight value, this is my error. Okay. We have calculated this thing. Okay. And I told you slope of a line is represented like this. So the calculation that you did is actually the slope of a tangent passing through this particular point. What you calculated? You have calculated this thing, slope of a tangent that is passing through this particular point. All right. Okay. This curve is representing what? Change of error with respect to weight. Okay. Now at a particular point, you calculate, that means you are just picking a very small point. Okay. So if there is a curve, okay, and on a curve we know we can have a tangent. So the slope of a tangent actually you calculated using this. Slope of any line can be, if a line like this, okay, it will have a
But how come it's a tangent? Because it's not touching x.
It is not touching x.
I mean, the slope which you made, like y is equal to x square, So x square is not touching the x line. So tangent is when it touches the line of a line. I mean, whether it's any line, it passes through the line, touches the line.
See, if we have a curve like this, then this is called. Oh, sorry.
Yeah, yeah.
If we have a curve, then this is called tangent, right?
Correct, correct. But here, why this curve is not touching x, right? I mean, here in your picture, in your diagram.
X, it is not touching. Like
Curve
why it should
you have made, the curve that you have made.
I'm talking about this. I'm talking about this line.
Okay, okay. But still,
This is a tangent, right?
Tangent. Okay. Yeah, hypothetically, yes. X and Y meet here. Yes.
No, no. See, why hypothetical? This line is a tangent of this curve, right? Okay, let me just do it once again.
X,
No problem, no problem. Let me just try to do it once again. Delete it. Okay. See, here I have error value. Here I have weight. Okay. According to this equation, E is equals to this one. Error and weight will have a this kind of a structure. Okay, because y is equal to x square is having similar structure. Now, as error is changing, like when weights you are changing, error value is changing. Whenever you are changing weights, error value is changing. Right. I want to find out that particular weight for which error is minimum, right? This is what I want. So how can I find it out? Okay, what's the process to find it out? The process is start with any random value of weight. Okay. So let's say I started with this particular weight. Okay. So because of this weight value, I got an error over here like this. Okay. This is my error value. Okay. So that we can calculate using this one. Using this equation, I can calculate. Right. Now what we did at this point, we calculated the gradient. So gradient actually represents the slope of a tangent that passes through the curve. The slope of the tangent that is passing through the curve from this particular point.
Right. X square minus y square upon x square.
So this tangent, okay, this is represented by what you calculated over here. All right. Because this is what? This is actually the change in area of this one, which is E2 minus E1 upon W2 minus W1. This is actually the slope of any line. This is slope of any line, right? But here the line is passing through a point on a curve. So this is a slope of this tangent. This gradient is representing the slope of this tangent. Now, a line can have what? 4 possibility. If there is a line like this, in which y value is decreasing and x value is increasing. Equation says y2 minus y1, x2 minus x1. That means this line will have a negative slope. All right. If a line like this will have a positive slope. A horizontal line will have a 0 slope. A vertical line will have an infinite slope. Okay. So based on this thing, we can say this line will have a negative slope. So now what we do, we will tune the value of weight. Weight is equals to weight minus this thing. I know that this line will get a negative slope. So weight minus something negative. That means this is equals to this one. That means next value of weight will be towards right hand side because it is increasing. So next value of weight will be over here, for example. Okay. So at this point, again, we do the same process. Same process means what? Again, there will be a gradient calculated, right? And that gradient will represent the slope of a tangent on this curve, right? As it will represent the slope of the tangent at this curve, again, you can implement it over here. It will have a negative value, and this will again increase or let you move towards this direction. You touch over here. Here again, you do the same process. That means again, there can be a like this, right? And again here you will calculate the same thing, and then again you move towards. So slowly, as it's like, sliding on a curve. Okay, slowly as you move towards the minima, okay, at the minima automatically it will have a horizontal line. Okay, this gradient will represent this gradient you calculate at the minima, okay, will represent a horizontal line whose slope is almost zero. As it is almost zero, this entity is almost zero, the weight will not change anymore. Okay, and you touch the minima, right? What if you started from here? Nothing to worry. Suppose your first initial point is over here. Okay, that means over here also you have a slope. Like this. All right. So this slope is positive in nature. This particular tangent will have a slope positive. Okay, this tangent will have a slope positive. That means weight is equals to weight minus d upon dw, which is equals to weight minus some positive value, right? That means next weight will be on the left hand side. Okay, and again over here you'll calculate the same thing, okay, and do the similar process. Then you will again left hand side. So whatever the side you are starting, okay, this process will slowly take you towards the minima, and at the minima it automatically stops because gradient value will be 0. All right, so that is called what? Gradient descent of error optimization. That means start randomly with any particular value of weights, and then let the algorithm identify the best possible
minima is the mean, or minima is the mean, right? X minima.
Minima is the minimum. Minima is minimum value of
X,
error.
where the error is the least.
Right. Okay. Minima is what? Minima is the minimum value of error, or you can say where the error value is what? So here it's like you have this thing, okay, right? And slowly here you have a gradient, okay. The value of this gradient is what? dE. This is cost. Cost means what? Error. This is weight. dE upon dW, because these two things we have on the x and y axis, okay. And this line, okay, if I have to find out the equation of this line, sorry, slope of this line, what I have to do? I have to use E2 minus E1 upon W2 minus W1, because it is on y-axis is E and x-axis is weight, right? So the same thing we're calculating over here, but with the help of this curve, okay. So same thing we calculated for this particular point, and then we applied weight is equals to weight minus, okay, because of which we move towards the left, and slowly at the minima this entity will automatically become 0. As it becomes 0, weight will not change, and then you will have the best trained parameter. Okay, so let's try to check this thing practically so that we can understand how it actually functions, right? So I'll put it over here. Okay, both the things side by side so that we can easily understand what is going on, right? So I have error calculated, right? This is our error value. Okay. With this error, we'll calculate the gradient. How can you calculate gradient? dE, let's say W naught. This is equals to what? Negative of 2 multiplied by y minus YH. Okay. So this is what my gradient. Okay. Now it is a gradient for all the 5 points. So we'll take the mean of it. Okay. Now we'll have the, because mean of error also we are using. Right. Thereafter, let's say we'll calculate over here the next gradient, that is minus 2 multiplied by y minus YH multiplied by what? X. Okay. And then we can take the mean of it. Okay. So two gradients are there. Once we have these two gradients, what we said, we can apply over here. Okay. This is what we can do, right? Isn't it? So let's try to do it. Weight naught is equals to weight naught minus DEW naught. Okay. And weight 1 is equals to weight 1 minus DEW1. Okay. So now we have two weights that we are trying to update. Okay. So print weight naught and weight 1. Okay. So these are the two weights we have that we try to update. So it is updated. Now based on these weights, shall I again calculate YH? Let's calculate YH. And based on this YH, I'll calculate the error. No need to print YH, directly print error. So what happened? My error value, which was 4.8, and it is supposed to decrease, it increased to 3875. All right. What's the reason behind it? The reason is unregulated training. Okay. During the training process, regulation or regularizing. Okay. Regularizing the training is also very important. Like suppose if you are driving a car. Okay. So you can't just start and just keep accelerating. No, you can't do that, right? You have to identify, according to situation, you have to identify optimized speed. Then only you can drive better. During the machine learning training also, the regularization is very important. It's not like that you can just let the system work in with any speed. So here we have to regulate. Okay, why we need to regulate? See, we have calculated over here something called gradient, right? Let me just try to explain it over here. See, here we have calculated something called gradient. Okay, gradient is being calculated, which is a slope of a tangent passing through this curve. A curve which is a result of y minus y hat square. Okay, and slope of a tangent passing through this curve is the is gradient. Okay, this is what we calculated over here, 3.2, 26.8, whatever. Right. Now, this thing is giving me the direction that I have to move this side to minimize. Okay, if it is over here, so this will give me the direction that I have to move in this side to minimize the error. Okay, but along with the direction, these guys are also giving me the magnitude, right? They're having some magnitudes like 26.8 or something. Okay, what it means? Let's say my initial weight value was 1. Next weight value was what? The updated weight will be what? 1 minus 26.8. Because we are using which formula? Weight is equals to weight minus, right? So next value is minus 25.8, something like this. That's a huge change. From 1, you just jump to kind of a value which is not it's not work, because I have to do what? To optimize my error or to reach the minima, what I need baby steps. Okay, then only I can touch the minima, right? If I will not take the baby step, if I'll go with the unregulated training, it means what? From here, okay, like see, from here you are jumping to some point like this, okay, and then like from here you jump over here, and from here you may jump over here, right? So that will not work. Okay, like for example, if you will see in the gradient descent thing, there is over here, you are having this kind of scenario right now. Okay, so if your training is not regulated, your gradient descent can't take you to the minima, right? So how it can be regulated? It can be regulated with the help of learning rate. Okay, learning rate. What is learning rate? Simple. Let's see. See here, we are using weight is equals to weight minus this one. Okay. So if my weight value is 1, so if I use learning rate over here, let's say, just a minute. Okay, we try once again. Okay, so weight is equals to weight minus learning rate into this one. So it means what? 1 minus, let's say learning rate is 0.01 multiplied by 26.8. So it will do what? It will just control the magnitude. It will become a 0.26. The direction will remain as it is. So your change will be what? 0. What it is? 26. It could be. What will be the output over here? 8, 4, right? 1 minus 0.26 is what? 0.84 or 0.74? I guess 0.74, right? Can you tell me?
Yes.
0.74. So now the change is very small. You can see the last time change. Okay. Because of this, the change was very huge. Okay. 1 to minus 25.8. But now it is a small change. Okay. Now you're capable of taking the baby steps. Right. So here I have to apply something called learning rate, right? So here I'll assume a learning rate, let's say 0.01. Okay, and this learning rate, so learning rate is going to be like we are going to use for so many times, and it will be a kind of a hyperparameter. Okay, what is hyperparameter? The parameter that we decide. Okay, so here it is a kind of a hyperparameter that we are going to use for so many times. This will be used to regulate your training. Okay, that means your training can't be very fast and it can't be very slow. If it is very slow, it will take a lot of time to optimize, right? If it is very fast, then it will not optimize. Okay, so based on this learning rate, again, this is our YH, this is my initial error, this is my gradient, and based on the learning rate, I'm changing the gradient, very small change in the gradient. With this small change, you can see error changes and it reduced. Okay, from 4.8 it came down to what? 1.42. It means what? It means if I will implement this process again and again, like here I'll take it. Okay, let's say I have initial coefficients, right? I will do what? For I in range let's say I want to execute it for 20 times. Every time I have to calculate the value of y, and then with the value of y, I can calculate the value of error. Okay, right, and then I can print the value of error. Okay, so as of now, my error value will not change every time, it will remain same, because every time there is no change in coefficients. Okay, so now what I do, I will implement a process which can calculate the gradient first. Okay, this is a gradient of W naught, this is a gradient of W1. Okay, which can calculate the gradient first. Next, which can update the values of weights. Okay, and again run the, again it will go and calculate YH and again print the error. Okay, so now every time we are changing the value of weights, because of which if I'll execute, you can see the error value continuously decreasing, and after some time it is stopped decreasing. Right, so as it has stopped decreasing, why it has stopped decreasing? Because gradient may become very small. Okay, gradient becomes very small, that's why it is not decreasing much. All right, so here this is what? A squared error. Okay, if I want to calculate absolute error, what I can do? Absolute value of y minus YH dot mean print absolute error. 0.89. Last time what was the absolute error we got through least square method? 0.94. Okay, almost very close to that, even slightly lesser than that. Okay, so here we got the absolute error as 0.89. Okay, and what are our trained the coefficients W0 and W1? Okay, this is this one. Okay, 0.74, 2.01. What we calculated last time? (0.61), 3.01. Okay, so almost very close to that. Okay, based on this, I can I have already calculated YH. Okay, now I'll plot the YH PLT dot scatter x comma y PLT dot plot x comma YH, which is red in color. It is, I guess, capital X most probably, and then PLT dot so. So we get a best fit line, we get a coefficient, we get an intercept. Okay, how we got it? We started from a random value, that means random coefficient intercept, because we are having no idea. Okay, that's why it is called supervised learning. Okay, what it actually did, first it just used these values, okay, to calculate something. Right, now this one is compared with what? Actual y. Okay, which is given us the error. With the help of this error, we calculated the gradient. Okay, we just use the gradient over here, right? And this cyclic process continuously keep decreasing the gradient value. Why it keep decreasing the gradient value? Because you started from here, okay, and slowly you are moving on this curve. So as you move on this curve, after some time your gradient will be 0. Right, when it is 0, that is a minima, and after that error value will not change anymore. Okay, and this process helps us in finding out the best possible coefficient. So now the point is where it should be used. See, ordinarily least square for a simple problem statements with 1 or 2 features, but for a larger problem statement if you're going for the non-linearity, because later on you have to break the linearity as well. Everything can't do with the help of linearity. Okay, we have to go for non-linear as well, non-linearity or some complicated state of problems. So in that case, gradient descent will work better. So file already I had shared with you, please have a look. Okay, if anything you want me to discuss here, please let me know. But this is just for your understanding. Okay, you should, why you should know it, because later on you have to work with the this one, what is called learning rate, hyperparameter. So suppose I'm using learning rate, okay, and I'm deciding learning rate 0.01. So you should know what learning rate is. Okay, because we don't have to write this kind of code every time. We have to use libraries. But even using the libraries, it's fine, but you should know the underlying concept, that what is going on behind the scene. Okay, what libraries are doing. Okay, then only you can better optimize everything, isn't it?
Bipul, for learning rate, right? We consider the value 0.01. Like that is is it like we can consider any other value also, right? Why 0.01?
Good, right. See, here this is something which is kind of a tuning thing, right? You have to tune on your own. Okay, suppose if I use learning rate 0.1, okay, suppose let's say I'm using learning rate 1 over here. Okay, so my error value, instead of increasing, it started increasing. It is not decreasing because of uncontrolled gradients.
Okay,
It is very high. So as it is very high, you are not this kind of situation happened. Sorry, this kind of situation happened. Okay, now I make it 0.1. So now as I make it 0.1, it is still increasing. Right.
Okay.
So I will make it was 0.01. So now it started decreasing. See, either I should do it manually, that is one process, or I can also make like some, this is very simple code. I can make this code in a way that this will check the next error value and compare it with the previous error value. Okay. If the next error value is higher than the previous error value, right? So automatically learning rate decreased by one more decimal place.
Got it.
Okay?
Got it.
And if the next error value is lesser than the previous error value, then it will continue going for the, it will continue the loop.
Okay.
That kind of logic we can make, but that is not required because we have to use libraries, right?
Yeah.
So now if I can make it 0.00, yes, I can make it, no problem. But with this thing, the learning will become very slow. Isn't it? See, it is so slow that still it is not repeating the error. Okay. If you check 0.1 over here, after here, the error repetition is started. Almost same error value. But if I make it 0.04, it becomes so slow that still there is a chance of decreasing. That means with the more smaller learning rate, you have to increase the number of iterations. Okay. Right? Because learning becomes very slow. Right? So this is something that you can tune manually. That would be better. Otherwise, if your programming skills are good, you can also write a program. The logic I told you, if the next error is higher than the previous error, just decrease the learning rate by one more decimal place and then continue the loop, right? But since we have to use a library, so no need to do it like this, because this kind of code is not feasible if you are working with 10 or 20 features or 50 features. Because suppose you are working with 10 features, then there will be 10 gradients. Okay. And if you write the script in which you are calculating 10 gradients, optimizing gradient, the chance that you will do a lot of errors.
And when we are using the libraries and all, even then we have to mention a learning rate, right? Hyperparameters. So in that case also we are putting it when we are doing the actual model.
Correct.
We are doing the actual model. We are also mentioning the learning rate there, right? So there also we are mentioning it manually. So what's the difference between here putting it manually and there putting it manually? Because there you might also be changing the hyperparameters, which is one of the hyperparameters is your learning rate, which can be 0.01, 0.0011. We will see manually if the gradient is decreasing at a faster rate or slower rate, is it constant or not constant. There also we will define a learning rate, or it is automatically the system will calculate this is the optimized learning rate. Since we are using a library, we are using matplotlib to make the graph easier in 1 or 2 lines. Otherwise we can make the graph by ourselves, but it will take long. So are we in the libraries, the learning rate is also defined by default. It will take the best one.
Yeah. See, when we are using a library, there used to be a default learning rate that is there, which is 0.01. Okay. The default learning rate is there, 0.01 is defined, right? But sorry, 0.01, right? So based upon the, we'll train a model, and after training a model, we'll monitor its performance. Okay. And based upon that, we manually change it. Okay. We can make it 0. Suppose we think that this is quite high. Okay. So we can make it 0.001. Okay. We can make it 0. Or suppose it is slow. So we can make it 0.1. Okay. We increase or decrease. We both the things we do. Okay. We increase as well as decrease. So in which case we increase? Suppose you are using a normalized data. Normalized data means what? Your features column are having a value between 0 to 1, 0.3, 0.1, 0.5, 0.2, like this. So when you are using these kind of information, right, your gradient will be automatically very small, isn't it? Because you are using what? Like suppose in place of X here, we are using these kind of information, right? So YH will be small, right? So this kind of thing, your gradient is already small. So in that case, we keep the higher learning rate. We can use 1 or 2 like that. Okay. But in case when your magnitude of features are very huge, like here it is 3000, 7000, 5000. Okay. Then in that case, your gradient will also be huge. As gradient is huge, then we use a smaller learning rate. So, that we will tune according to situation. By monitoring the model performance, we have to tune on your own.
Here also we
Okay,
are
that's why it is called hyperparameter. There are two kinds of parameter. One is called hyperparameter, other is trainable parameters, right? So these guys are trainable parameters. Okay, that model is identifying during the course of training. Okay, and this is what hyperparameter that we define, isn't it? Am I clear?
yeah.
Okay. Yeah, it's not. We can also build some logic so that model can find out best hyperparameter, but that is a separate part of discussion. I'll come to that part. As of now, keep the thing simple, in which we know only two things. That is, one is hyperparameter, other is trainable parameter. Hyperparameter, we decide. Trainable parameters, model will find it out. Okay. Later on, we'll find some more information.
All that, right? Lasso
Yeah.
yes.
Correct. Okay, so now this is done, right? Now let's see how it can be used for our process, right? So here we'll work with the case study. Advertising. Okay. So here, this is done. Okay. So I have, let's say, X and Y, right? So here PLT dot scatter X comma Y PLT dot so this is a relation between X and Y. Okay, I want a best fit line. I know the equation of a line, that is YS is equal to W naught plus W1X. Okay, but this is not having W naught, and I have a X information known, which is TB expense, but I don't know W naught and W1. No problem. Just define it. W naught is equals to anything like suppose 4 or 5. W1, let's say this is defining 5, right? So based on that, YH will be calculated. Based on the YH, we can calculate error, Y minus YH whole square, and can take the sum of it. Okay, and then I can calculate what over here? The gradient. So dEW naught, that would be equals to what? Minus 2 multiplied by Y minus YH. Okay, dEW1, that would be equals to what? Minus 2 multiplied by Y minus YH into X. Okay, based on this, I can update the values of W naught. W naught is equals to W naught minus dEW naught, and W1 is equals to W1 minus dEW1. And here I can also use learning rate. Okay, learning rate, let's say 0.1, right? I don't know about learning rate, right? So I'll use only 0.1 over here, like this. Now this process needs to run in a loop, right? So I can do what? I can just put over for I in range, let's say 0,50, because you have more samples. Okay, and just put it over here, right? And then I also want to print the error. So print I comma error to monitor whether error is decreasing or not. Okay, so I'll execute it. So it is showing error is increasing. Let's make the learning rate smaller. You see it is increasing. Let's make it more smaller. Still it is increasing. Let's make it more smaller. Somewhere it is now controlled. It is increasing still, but controlled. Okay, now it is decreasing, isn't it? It is decreasing, but decreasing very slowly.
But the error is very, 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 very big, extremely big.
Take the sum of,
It's so big that you can't even read the numbers.
yeah, I take the sum actually. It should be right. Again, this gradient also I didn't took the mean. Okay, because multiple values are there, so I should take the mean over here, right? That's fine. Okay, so now you can see error value is decreasing, right? And
In slow pace. After 11, it's moving very slow.
no, that's fine.
Then it's decreasing. Then it's increasing. And
Yeah, yeah, it is decreasing, and we have a minimum error close to 12 point something. Okay.
After that, it's
Yeah. So at this point, if I will calculate over here the mean absolute error, how can I calculate mean absolute error? Y minus YH, absolute value of it, and dot B. It is coming out to be 2.88. So on an average, while if I use this process, okay, if I use this process to predict the value of sales, if I know the TV expense, okay, this is a best fit line, plt dot plot x comma yh. All right. So if I use this process, like I had calculated my trainable parameters like this. Okay. Now, if I use this process to predict the sales value, how can I predict the sales value? I need a TV expense. So suppose my TV expense is equals to 54.7. So my sales predicted can be equals to what? W naught plus W1 into TB expense. Okay, so now I can have print sales predicted. All right. Okay. Now one more important thing that I want to tell you. Okay. So can this minimum error be different if this value from where we are starting is different? Is it possible?
That should be different, I guess.
Yeah, this is actually okay.
Just defining it. We are defining it. We are making it fixed, static.
Yeah. So see, if the starting value I change to 5, 6. Okay. Now let's see what
It will
happens.
change, I guess.
My minimum error
Change.
becomes 1.58, right? And minimum mean absolute error is 2.65. It decreased, right? And if you see the plot will also change.
Slightly.
Slightly change. Not too much, but slightly change. Okay. It means what? It means from the point you are starting. Okay. That also, let's say, let me make it as I increase it, it changes. So let's increase it more. Let's 6.5. 10.79. It changes more. Okay, let's try to increase it more. 7. Okay, so still it is remaining same. Let's make it 9 or 8. Now it started increasing. Okay, that means the sweet spot, if I can say, was 6 and 6.5 over here. Okay, on which we are getting the minimum error. Now, why it is changing like this? If I am kind of changing the initial value of weights, my final minimum error is changing. Why is it so? It is because the gradient descent actually works in this form. Okay, now if this is not clear, let me tell you, it works like this. Okay, because we have multiple, we don't have a single coefficients, like this is an equation of what? If I use y equal to x square, that means y is only depend upon x square. Okay, but here we have y is equal to w naught plus w1 x square. Sorry, y okay, w naught x, right? And then we are calculating error is equals to y minus y hat. That means this error is dependent upon multiple things. Okay, multiple like w naught, w1. So we can't expect the ideal curve like this. Okay, so the curve will be affected by multiple coefficients. Suppose I am working with two features. Okay, so the equation will become what? X1 and x2, right? So now this curve will be affected by all these three components. So I can't expect it to be ideal like this, right? So it will form a lot of minima. Okay, and out of a lot of minima, there is one minima that is called global minima, where my error is minimum, right? Because suppose you started your training from here, your training start and it will stop over here, because here also I have a horizontal slope, right? Your training may stop over here, here also I have a horizontal slope. Okay, your training, you start from here, your training may stop over here, which is a horizontal slope. So out of all the possibility, this one we required, so that we can, the minima we can get by slightly changing the initial weight value. Okay, if I slightly change the initial weight value, I can get the minima easily. Am I clear?
Yes, yes.
Okay, so this is what we did. Now this is the simple linear regression. What if I am working with a multiple linear regression? So multiple linear regression, nothing to worry. multiple linear regression. What it means? It means that we can just take over x is equals to df of TV and radio. All right. Y is equals to what? df of sales. Okay. So now your equation says what? Y is equals to W0 plus W1 into X1 plus W2 into X2. That's it. Right. This is a change. Right. So according to that, gradient will be changed. Right. Like we have over here, Y hat is equal to W0 plus W1 X1 plus W2 X2. So error will be equals to what? Y minus Y hat whole square. This can be written as Y minus W0 plus W1 X plus W2 X2 whole square. This equals to Y minus W0 minus W1 X1 minus W2 X2. All right. Whole square. That means if you calculate gradient, this will be equals to what? Minus of 2 Y minus this whole thing we can write as it is Y hat. It is minus 1. So minus 1 already goes over there. Okay. If I calculate for W1, it would be what? Minus of 2 Y minus Y hat. It is X1 is there. So X1, this minus came over here. D upon D2 is minus of 2 Y minus Y hat X2. All right. Am I clear? Okay. So this process I have to apply same thing that we did, same process I have to apply over here. Nothing changed, only for two features. Okay. So what we do, we will calculate over. We will just define W0. Let it be 3. W1. Let it be 4. W2. Let it be 5. Okay. So based on that, I can calculate this thing. Okay. Where x1 is what? X dot TV component. X2 is what? X dot radio component. All right. Thereafter, I can calculate error. That would be equals to what? Y minus YH whole square, and then I can take the sum mean of it. All right. Then we can calculate what? The other things, right? So let's calculate DE W0, DE W1, DE W2. Okay. What is this? This will be equals to minus 2 multiplied by what? Y minus YH, right? Y minus
YH.
okay. And then we can take the average of it, right? Okay. Because this is for intercept. Now minus 2 multiplied by okay, if I don't take a square of error, okay, since we are considering a square of error, that's why this minus 2 is coming. Okay, if I don't take, then this will not come. Even if you don't use minus 2, it will not affect. Only minus sign is important. 2 is not important. Okay, because 2 is constant. Okay, if you remove the 2, what will happen? The learning process will slow down. Okay, the learning process will slow down. That's it. Right. So same thing, I'll just take it from here and will copy and paste it for all these guys. And I'll make a small change. What is that? For this guy, X1 will come. That is your X.TV. Okay. And for this guy, X.radio. That's it. I hope everything is done right. Now, based on this, I can tune the values of weight. So before tuning the value of weight, I need learning rate. Learning rate, I don't know, so I'll use 1 over here. And then I'll use W naught is equals to W naught minus learning rate into DEW naught. Okay, and then W1 and then W2. I hope this is done. Okay, and based on this, I can do that. Now you know that these things I need to do in a loop. So we'll do for I in range. Let's say this time I'll go it for 100 times because I have 2 features. Okay, and every time I'll print the error over here. So now you can see error value is increasing a lot. Decrease the learning rate 0.1. Still not helpful 0.01. Not helpful, right? 0.000. Let me use 230. Still now it is decreasing, right? Decreasing little slowly. Let me make it 10 I remove, but when I removed 10 it started increasing. That means that is the best. So it is decreasing, but it has a scope of more decrement. So 100 iterations may not be enough, isn't it? So as 100 iterations is not enough, we can make it 500 iterations. Okay, it has a scope of more decrement. Up to 2 decimal place, if it repeated, then we can say we attained minima, right? So it is not up to 2 decimal places, right? So let's make it 1000 iterations. 2.7. Now it is almost at the minima, right? So now my average, that means the mean square error is 2.79. Now few things we have to identify. What are trained parameters? Okay. Second, what is minimum? What is mean absolute error? Okay. And the next thing, prediction. So trained parameters are very simple. Here I have 3 trained parameters: W0, W1, and W2. All right. What is mean absolute error? It is Y minus YH, absolute value of it, dot mean. Okay. And we have to make a prediction. So how can we make a prediction? Let's take a value from here. Like last time we make a prediction, right? Like this, okay? So same way I can make the prediction. Okay, but this time to make a prediction, we have W0, W1, and I also required what? Radio expense. $87.4 something. Just randomly I pick any radio expense and plus W2 into all right. So the point over here is like when we are using 2 features to train the model, my error value came down to 1.24, which was 2.5 when I used only TB expense. Isn't it? With the TB expense, it was 2.5. With the TB radio, it came down to 1. That means model performance improved. Am I clear?
Yes.
Okay. So now, what actually we have to do? Like this is good for understanding learning rate and everything that we had seen, right? But in general, we have to use the scikit-learn linear regression library. Okay. Every time you can't write such code, if your feature size is very huge, there is no point of writing that kind of code. Okay. So here we will use this inbuilt library, right? And we'll ask this thing to do the job. Okay. So how to use it? Just have this thing and you can use it. Let me show you. Scikit-learn for okay. So first we require data. We already have a data. First, go with the simple linear regression. All right. Simple linear regression is what? X is equals to one of the component like df of TV. Y is equal to what? df of sales. Okay. Then we have to import the algorithm. So from sklearn dot linear model, import linear regression. Then I define model A, that would be equals to what? Linear regression. So what I did, let me tell you. First, I import a algorithm. Okay, from the inbuilt library. Import algorithm from inbuilt library. Okay, and this is what define model to be trained. Define your model to be trained. All right. Thereafter, model A dot fit x comma y. Clear? So when we fit it, my model get trained. Okay, but it is saying an error that require two-dimensional. What it means? See, here I am using inbuilt library. So as I am using the inbuilt library, so we should kind of follow the process that is expected over here. Okay, so it requires two-dimensional data. So take it two brackets. Train the model. So once your model get trained, you will have what? The training coefficients or trained coefficient, right? So you can identify it like this. Model A dot coefficient and print model A dot intercept. Right? So what are we getting? 0.04 and 7.03. Is it the same trained coefficients and intercept that we got earlier? Can you check once? Here we got 5.96 and 0.05. Right? And what are we getting here? Almost very close. Okay. Next, we'll try to predict and calculate error. So model A dot predict on given X. So this is a predicted value of sales. Okay. So I can call it what? YP. Okay. That is a predicted value of the sales. Okay. Now, the difference between the real sales minus YP, we get it over here. What is the average error? absolute value dot mean. Okay, so here my mean absolute error is equals to what? What? 2.54. Is it very close to the mean absolute error that we got earlier? What we got earlier? When I used single component, that is your single TB and sales, that is when we work on the simple linear regression, my mean absolute error was 2.54. When I use this thing, that is your inbuilt algorithm scikit-learn, in the scikit-learn I had given my x and y, and this thing get trained using linear regression, and at the end we get the same level of average error. Understood?
Yeah,
Predicted it.
we are using single feature only, right?
Right. Okay, let's work on the prediction as well. So this is what we predicted earlier, right? So I'll copy this part and we'll put it over here. Okay, now for the sales predicted, this is our coefficient.
Intercept. That's the coefficient.
Yeah, this is your intercept, right? So I'll put it over here. Okay, so this time it will make the prediction like this. So what is your prediction? 9.63. And what is your actual prediction? That means 8.86. So last time when you follow the gradient descent, it was, yeah, slight difference may be there. That's fine. That is not a big problem. Okay, it is just a slight difference may be there because of initial coefficients, right? And you can also make a prediction like this. No need to write the equation. Sales underscore predicted is equals to model A dot predict. Okay, so when you are using a library, you have two things to use. One is called fit. Fit will let the algorithm know about your data, and predict will let the model predict from the given data. Okay, so you want to predict from TB expense, that's it, get the same value. Okay, so what is your process? The process is very simple. Have your features and labels, pick your algorithm, fit it, and do it. See, machine learning is just 30% of whole process. Okay, 70% is data cleaning and data pre-processing. Okay, first you have to ensure the quality of data. Okay, once the quality of data is assured, that means you know that you are working with a good quality data. Later you can implement the machine learning algorithm, and machine learning algorithm will automatically give you the best relationship between features and labels.
One thing, right? So this line, right? YP model A dot predict X, right?
Mhm.
What is the output of this actually? Like, so if we get the coefficient and intercept, we can figure out the predicted value. But then when you're doing YP is equal to, like, when you're predicting it, like where do we see the output of this?
Okay, the output is over here. It is a predicted sales value
Yes.
for
Yes.
for all the existing data.
Got it.
Okay. Like X is what? X is the expenses made on TV advertisement.
Right.
Expenses made on TV advertisements. Okay. And sales is the sales value of the time or sales achieved. Right. So now when we build up a linear regression model, so using these things, okay, my linear regression model is predicting these are the sales. Okay,
Got
so
it.
what we do, we'll calculate the difference between the predicted sales and the actual sales we know.
Got it.
Okay, so that we can identify what is the average error that my model is currently having.
Got it.
So my model is having 2.54 of average error. It means for any new entity, suppose 54.7.
Okay.
So for 54.7 TV expense, if this is my sales predicted value, so I can consider that most probably the error will be in the range of plus minus 2.54. Right?
Got it.
That means the actual sales may exist between 7 to
12.
12. Right.
Correct. Okay. Got it. Thank you.
Another thing, this average error, 2.5 is a very big error, right? So what is this?
We'll discuss. Don't worry.
Yeah.
We'll make it.
Then we have to maybe take some other model in order to minimize the average
We'll
error.
tune it. No other model. I'll tell you so many tuning process, right?
Okay.
Don't worry about it. I'll explain. Right? It's like there are so many ways are there through which we are going to tune these things.
Correct. X and Y, maybe 70-30 or maybe something, maybe Lasso method. Maybe some hyperparameters we changed in order to bring down the average error. Like
right.
One, close to 1, or maybe close to maybe lesser than 1.
Right. Okay, so shall we continue, or you want to go through the things a little more?
This. I'm ready. I'm okay.
You're okay? Okay. So see, now the point over here is when we train this model, okay, and we are kind of evaluating its performance. What are we doing? We are using the same components for training and evaluating. Okay, that means same X and Y. Okay, this is your X and Y we had used for the training. Okay, and same X and Y later we just predicted on X. Okay, and that predicted value YP we compared with Y to identify its error value. Okay, so this is not a very kind of a good idea to use the same data for training and evaluation both. Why? Because we don't know how will it perform if some unknown data will be given to it. Okay, unknown means what? A data which the model had not seen before. Okay, because model had seen all these data before. Okay, and we are predicting on the same data that it had seen before. Okay, model had seen all the values in X, right? And we are again predicting on the same data that model had already gone through during the process of training, right? So we don't know how will it perform if something new will come to it. Okay, so to ensure that part, what we do, we basically divide the data in two parts.
Training and
train and test part, right? So when we have features enabled, the next step that we follow over here, divide the data into training and test sets. Okay, generally the majority portion of the data used to be training data. Okay, that means we can use 75 to 80% of the data can be training data. Okay, and thereafter 20 to 25% of data can be a test data, isn't it? So how we do it? We'll again make use of from miscellaneous dot model selection
Train and test. Yeah.
import train test split. Okay, x train, x test, y train, y test. That would be equals to what?
Train and test.
X comma y. Then we can define the shape of it. Let's say train size is equals to, let me have 0. Say, like suppose 75% data in training, so 0.75. Okay. So what will happen? Your training data will be divided. If you check your data shape over here, train x dot shape and y dot shape. Okay, so this is 200, right? But after splitting, x train and x test. After splitting, we have what? Only 75% went to training and 25% is now in test. Okay, that means now when we want to train your model, we will not use the whole data that we have. Now we are using only 75% of the data for the training. Okay, and these are coefficient. And then when it comes for evaluation, we make a prediction on training data. We'll store it into y train predict. Okay, and we'll also make a prediction on the test data. Y test predict. Right. So training was done on one set of data. Okay, that is 75%. But prediction we are making on both the data separately. Right, so that we can evaluate their performance separately. Train mean absolute error will be what? Train mean absolute error will be the training data label, that is y train, minus the training data predicted value. Okay, so this is what train mean absolute error. Okay, now we compare the test mean absolute error, that whether the test error is close to it or is it not close to it. Okay, so what we do, we will just use our test mean absolute error, that would be equals to what? Absolute value of actual label minus the predicted label dot mean. All right, so this is what print test mean absolute error. Am I clear? Right, so what it means, that means my error value will remain in the range of 2.3 to 3. Obviously it is high, we'll just tune it, right? If suppose my mean absolute error is very low, okay, see, if I'll again execute it once again, one more thing that I should tell you, this splitting is actually random. Okay, which means if I'll again split it, the data for train and test will change, and that's why the mean absolute error will also change. Right, you can fix it by using a constant for random state. Random state is equals to 1, so it will not change further, it will remain whatever it will get, it will remain that, right? So here this comparison is very important. It gives an idea that your train and test is almost performing well. That means on the known, not means close, not well, close. Okay, so on the train data the average error is 2.5 and on the test also it is 2.5. That means for the known and unknown, both the information model is performing very close. If it is not like that, suppose for the train you are getting an error 0.5 and for test you are getting 2.5, it means what? It means it is a overfit model. It is a overfit model which learned the train data very well. Okay, suppose this is train error. Again, this is your test error. Okay, it means what? It's a overfit model which learns the train data so well that it kind of memorizes it. Okay, it is not good for making the prediction. It memorizes each component that we had given to it. Right, that's why we need to evaluate, train and test both, so that we can check how is it performing on the known information and how is it performing on the unknown information. Rest it is fine.
And what overfitting is when the train data is error is very less, and uh, uh, the test data has a larger error. So what if the other way around, the train has a bigger error and the test has a lower error? So it is called as underfitting, or what is the
No,
term?
no. See, always your model will have the list error on the data which is used for training, right?
Yeah, training.
Like a data which is not used for training, like a data which is like, if a model is not performing well, suppose if it is, if a model is not performing well on the train data only.
Yeah,
Okay, train data is what?
obviously
Is
the error, it is that the model is not good. Obviously that we can.
right, right. So if it will not perform well on the known data, right, that means it will definitely not perform on the unknown data.
Of course, 100%. But maybe because it is a mathematical calculation at the end of the day. So maybe it does not make sense, but still it gives a very less.
And that is called underfit model actually. If
That's good.
your, yeah, the like your train data error is very low or accuracy is not so, sorry, train data error is very high, accuracy is very low, it is not working good. So obviously that is an underfit model. Underfit model is like, you know, it didn't find out enough number of trainable parameters to give you the good accuracy.
Right, right.
So that overfitting, underfitting, I'll explain when such scenario will happen. Okay.
Exactly.
At a higher level, it is like this. Suppose your data is like this. Okay. And suppose this is your size of your information. Okay. And you created a model like this. This will create an overfit model. Okay. But suppose your size of information is like this. Okay. And you created a model like this. So this is your underfit model. Right. At a high level you should know it. It's like, so the balance between the size of data, features and the model is very important. So those kind of balancing we'll see.
We'll see.
As of now, no need to worry about it. We'll come to
And
that part, right?
another thing, can you go to sir about the X train, the variables that you have put just a little above? Scroll. Exactly. So I understand this. You have to you define the variables, but can you? I just want to understand how Python uses all the variables together. I get always confused. It is not about the training spread. It's about the syntax of Python. X train, X test. We have all the variables, 4 we have defined here, and then we are calling a function with X and
All
Y.
right.
Very
Okay, fine.
confusing again. Instead of
I'll tell you.
separately putting it, it's very confusing.
Understood. See what happened when you are using this inbuilt function, right? Sorry. When you are using this inbuilt function, okay, I have not given any train size, nothing. And by default, also train size is 75%. Okay, you can change it to 80%, 90%.
Yeah. That's fine. That's fine.
So now when I execute it, so it had given me the output over here. When I executed it, you can see this is the first block. Okay, I scroll up. This is a second block. Okay, I scroll up. Thereafter, this is a third block. Okay, I scroll up. Something is missing. This is our 150 rows. Okay, fine. If you see, this is 150 rows, right? First block, right? Thereafter, I have again TB mentioned. Okay, if I scroll down, scroll down,
150, I guess.
it is total 50.
Multiple 150s. It will take randomly. It will it out of this it will it's I mean,
Just let me complete. Let me complete. So first 150 was separated. 150 TB components are separated over here. Next again 50. Again you can see TB. Next 50 random samples will be picked up because 25%. Okay, 50 random samples are picked up again in the TB over here. From here to scroll down. And once it is done, thereafter it is taking the sales component. Okay. So sales component also over here only, right? It's like, everything, so many data is there, that's why they combine. And then again 50 sales component like this. Okay, so it is doing what? Let me just tell you. This function actually divides x into two parts: x train having 75%, x test having 25%, right? And then y will be divided in two parts: y train
similar.
okay, so I just need to store them into 4 different variables. I just need to store them into 4 different variables. So if I want to store them into 4 different variables, I just need to give them in this particular pattern. That first train, test, x train, x test, y train, y test kind of thing.
So in Python syntax, can we do a comma b comma c comma d is equals to 1 comma 2 comma 3 comma 4? So
Yeah.
so one is so a is equal to 1, b is equal to 2, c is equals to, that is I was saying.
Correct.
Asking the syntax.
Correct. This is possible, right? Okay, so a is 4, b is 3, c is 5, like this.
Okay, and when we put that function, it will also work like that.
Right.
Test is the method.
Correct. So this function is returning 4 components. We are just storing into 4 different variables.
Right.
All right. Okay. So this was your simple linear regression. Okay. Next, we will explore the multiple linear regression. So multiple linear regression is what? Using 2 components, right? So
Yes.
x is equals to df of TV and radio. Okay. Y is equals to what? Okay. Y is equals to what? df of sales. Okay. And thereafter, I can split it from sklearn dot model selection import train
Test
x train x test y train y test. Okay, x comma y. Thereafter, what I can do, I can import the algorithm. So from sklearn dot linear model import linear regression. So model B is equals to what? Linear regression. Okay. Then I'll fit it. So model B dot fit x train comma y train. Okay. So once the training will be done, I need what? I need to evaluate. So evaluation will be done in 2 phases: training data evaluation, test data evaluation.
Yes.
So y train predicted value and y test predicted value. So predicted value on the training data, model B dot predict x train. Okay, and predicted value on the test data. Okay, then I have to compare with the real value. Very simple: mean absolute error for the train and mean absolute error for the test. All right. So how can you calculate it? MAE, the difference between your Y train
Minus predict.
minus,
Train.
here I should use ABS. Okay, Y test minus
Y test predict mean.
okay.
Predict mean.
So
And then
train,
we will just see which one
yeah.
is.
So train mean absolute error. I just did everything in one go because I hope you can understand what are we doing, right? Like in case if it anything which is not clear, you can let me know, right? Okay, here it is a test absolute error. If any part of it which is not clear, okay, please do let me know that what you can ask like what I did here, what I did here, right? I'll explain that part. So now it came down to 1.24. It means the second component in my data is really very important. That's why my error came down, right? Earlier it was 2.5, isn't it? Okay.
Right.
So is it like if I use newspaper, it will come down more? Let's check. Copy this whole thing, paste it over here, just add newspaper. Okay. Here I'll use model C.
But sir, here we did not do the split. 70, 75, 80, 20.
See, by default, split is 75% and 25%, right?
Okay.
So here we did it, right? You can see we have a X and Y, and then we split it, right?
Okay. By default is 70, 30.
Yes, by default 75, 25. You can define on, if you define on, let's see, I'll show you. Train test split. Okay, so if you see over here, see, test size if float should be between 0 to n represent the portion of data set to include in test split. If int represent the absolute number of ten, if none, the value is set to the complement of train size. If train size is also none, it will be set to 0.25. By default, it is 0.25. That means if the test is 0.25, then train will remain 0.75, right?
Of course.
This is a default value. If you don't define, then also it will work. Right? So here we are training on what? Only the train part, right? Now I take all three components. Splitting is done. Model C is defined, and here just the model name I am changing. Rest everything remains same. Okay. So here it is XY, splitting, model, fit, prediction made on train data, prediction made on test data, difference between real and predicted value for the train data, difference between real and predicted value for the test data, mean absolute error, execute. So we had seen one very interesting pattern over here. When I used only the TB component, my average error was close to 2.5. When I
More
used
the features, less the error.
When I use TB and radio, it came down to 1.2. Okay, but when I use TV, radio, and newspaper, okay, it remains close to same 1.2, 1.3. That means this time it didn't decrease. Okay, so these kind of things lead you to the prescriptive analysis. Okay, this is predictive and then prescriptive. Like you can now tell that which component in the data is actually important for sales prediction. Okay, with this thing we can say that TB and radio is important component, but newspaper is not an important component. And here actually the importance of correlation you can understand. Okay, if you call the correlations, you can see over here, these two are highly correlated to sales, but this thing is less correlated. So as this is less correlated, automatically your linear regression algorithm had given a least weightage to the newspaper. All right, and that's why even after adding the newspaper, your model performance is not improving.
Also similar.
Okay, you want to check the weightage of each of them. You can check it like this: model C dot coefficient. Okay, so this is your weightage of TV, radio, and for newspaper. It is almost close to 0. All right, and even it is negative.
Negative.
That means your newspaper, whatever the newspaper complex, suppose if you have to make the prediction. So you have TV, let's say 95, 90, radio, let's say 75, newspaper, let's say 2000. So now 2000 multiplied by 0.005 something, 6. Okay, whatever. So this 2000 will become 0.00 something 2, right? Isn't it? This value will become so small to predict the sales. That means it is not actually affecting the sales anyhow. Okay. So now this is what we'll discuss in more detail in the next class. I have just given an initial intuition. Okay. If I check the coefficient over here. Okay. So in the next class, what are we going to discuss? We are going to understand how this correlation can be helpful to decide or do the feature selection. Okay, and based upon the best possible feature, best existing feature, we'll try to train the model. We'll also discuss multi-collinearity. We'll discuss non-linearity. Okay, how non-linearity can be used, as well as we'll try to finish the project that we started over here. All right, we had started with the machine learning, right? So in machine learning, we first focused on regression. The classification will come to that later. Okay, nothing to worry about that. So in regression, what we need to understand over here, that this particular process of machine learning is used to build a model which can predict the continuous value. All right, which can just make a prediction about a continuous value, like in a kind of, like suppose from sales value prediction, salary prediction, right? These kind of things. Okay, property price predictions, these kind of things, isn't it? That is what we can do through regression. Now, while working on it, we first started with simple linear regression. Okay, simple linear regression. So what is simple linear regression? Simple linear regression is like when you have two components. Okay, one of the component you are considering as a feature, okay, let's say X, and the other component you are considering as a label, that is, let's say Y, or target. Okay, like for example, if you have to predict a salary, so for predicting a salary you are considering year of experience, right? And thereafter your final, just a minute, let me admit Varun. Okay, so let's say suppose you have to predict the salary. So for predicting salary, what you do, you consider year of experience as X, which is an independent variable, and this is your Y, right? So let's say year of experience is 3 years, 7 year, 5 year, 2 year, 9 year, 10 year. So salary we have, okay, let's say 50,000, 100,000, right? You can say, okay, fine, like this. Okay, 50,000, 100,000, right? 70,000. Okay, let's say 25,000. Okay, let's say 120,000. Okay, let's say 200,000. So suppose this is these kind of informations we have. Based on it, I want to predict the possible salary of a person based on the year, right? So when we have only one component, right, only one independent variable and only one target, we consider simple linear regression. What simple linear regression does, it will just find out the best possible linear relationship between the given set of features and target. Okay, whatever the features you had given over here, right, in your data, and whatever target you have, so that it will find out the best possible linear relationship. Okay, so that using that linear relationship in future, okay, you can forecast or predict a value. Okay, let's say suppose now you know the year of experience, using this linear line you can predict what can be the possible salary, right? So if you can successfully find out a linear line, it means what you find? You find the component of a linear equation, right? So in this linear equation, we have what? W naught and W1, and there is something called X. What is X? X is already given to us, right? X is already given to us over here, right? So for different values of X, whatever the X we have, okay, that we can feed here, let's say here I'll feed, let's say W naught plus W1 into X3, okay. Then we are feeding over here, let's say W naught plus W1 into 7, right? So now this, in this equation, X can be replaced by these values. Now from where these guys will come, W naught and W1. These are called trainable parameters, okay. So these value we don't know, right? And that's what machine needs to find out. That is called learning process, okay. Machine try to find out these particular coefficients, right? So it would be like this. Let's say suppose it is considering W naught as 1, okay, and W1 as what? 1. So it will be what? Here y hat will be what? 1 plus 3, that is 4. If these both are 1, right? If these are 1, then it will be 8, right? So that is called y hat. As you asked, Kaustubh, it is called y hat. Y hat is what? The calculated value of a linear equation based upon a defined coefficient.
Okay.
Right? This is called y. So now we will have y hat for all of these. Like for example, let's say for all of these things, I'll write it over here.
This is for a single feature, right? Single.
Right. Okay.
So,
So it's like
we are
for
talking about right now. We are talking about only simple linear regression because I just
simple
joined
linear.
it.
Right. I'm just giving you the revisit like what we did in last class. Okay. Nothing new. Whatever you covered, the same thing. I'm just kind of okay. So for the first thing, it is 4. For the second guy, it is 8. For the next one, using the same equation, it can be 6. Here it can be what? 3. It can be 10. It can be 11. Right. So now we have y and we have y hat we present with us. Okay. So based upon these guys, what can we do? Just a minute. Okay. So based upon these guys, we can calculate over here error. Okay. So what is the error over here? 50 minus 4. 50 minus 4 is what over here? I guess 46, right? Okay. Here 100 minus 8 will be what? 100 minus 8, I guess it will be
92.
Yeah. 70 minus 6, 64. Okay. 25 minus 3, 22. This is 110. This is what? 100.
189.
Okay. So this is what error, right? Right. Thank you. So in the next cycle, what happened? Your error optimization process will try to minimize these error as less as possible. And how minimization is possible? Minimization can only be done by tuning these things, right? These coefficient needs to be tuned, and that's what I explained how these coefficients can be tuned. Okay, these can be tuned through what? Gradient descent process, isn't it? Like after you calculated the error, what we'll do? We'll just have the gradient descent. So what we did for calculating the error? E is equals to y minus y hat. Okay, we'll take the square of it because sometimes it may possible your y hat may be lesser than actual y. Sometimes it is more, sometimes it is less. Okay, so here it is lesser, so it is positive. Suppose sometimes it is lesser, like suppose it is 25,000. Okay, and your y hat becomes suppose 50,000. Okay, actual value is 25, your y hat becomes 50, so it would be negative, right? this may be negative, right? So just to have all of them positive, we just take the square of it, and we also optimize it faster, right? Because if we penalize the error more, okay, if we are just kind of optimizing actual error, optimization will be slower, but if we penalize it more, optimization will be faster. So we calculate the error like this. Now this thing, if I look at this whole equation, this is similar to the equation y is equal to x square, right? That means this equation can form a curve like this, because this is a curve of y is equal to x square. Okay, if you see over here, y is equal to x square graph. Okay, y is equal to x square graph. So this thing represent y is equal to x square graph. Okay, if you keep changing the value of x, okay, like suppose x1, x2, x3, x4, x5, so you get this kind of graph, right? So as it is similar to this equation, right? So obviously we'll get this kind of graph, right? Now here what are we changing? So here it can be, in this equation you can change x and y will change. Okay, in this equation what you can change? Can you change y? Y we can't change, because y is coming with the data. Okay, this is y. Okay, this is coming from the data, so we can't change, right? So let's open up this equation. Y is equal to y minus, what is y hat? W naught plus W1x, because we are using linear equation. Okay, we are using linear equation over here because we are using linear regression, right? Best fit linear relationship, right? So it is a square over here. Y minus this one. This you can write like this: y minus W naught minus W1x, like this, right? So the E will change on what? Obviously y you can't change, x you can't change. What you can change? Only the coefficients you can change. Okay, so x axis can represent weight and this can represent error, right? So you can change this thing, that means weights and error will change, right? So we know this position is what we want, because here I have a minimum error. Okay, but suppose my initial weight is over here, right? So as my initial weight is over here, that means this is my initial error. Okay, so how can I find this particular spot where my error can be minimum? How can I find out this particular weight where my error can be minimum? I want this weight value where my error is minimum. So how can I find it out, right? So to find this thing out, what are we doing? We are applying a very simple process. We are just kind of differentiating it with respect to that factor which we have to change error. Okay, we can't differentiate it with respect to constant. Y is constant coming with the data, x is constant coming from the data features. We can't change it with that, right? So differentiating with respect to W naught will give me what? 2y minus W naught minus W1x. What is a constant with W naught? It is minus 1, so it is minus 1. You can write it like this: minus 2y minus y hat. Okay, y is actual value, y hat is calculated value based on some random weights values. Okay, same you can calculate the others. Okay, this will be equals to what? 2 y minus W naught minus W1x into minus of x. Okay, because minus of x is constant, is equals to minus 2 y minus y hat into x. All right, now if you look at this thing, E is your y axis, W is your x axis. Okay, this can be, you can consider like this: change in error with a small change in error with respect to a small change in weight. Okay, that means this is actually E2 minus E1 upon W2 minus W1. Okay, this is very similar to y2 minus y1 upon x2 minus x1. Okay, and this thing represents what? Slope of a linear line. Slope of a linear line. It means at whichever point you are calculating it, suppose you are over here, your initial weight is of, suppose this is my initial weight value 1 that we considered. It is my initial weight. Okay, so at this point, if you consider these things, That means actually you are calculating the tangent, the slope of the tangent passing through this point. What are you calculating? You are actually calculating the slope of the tangent passing through this point. All right. Now, if you look at this tangent, line can be like this. If there is a line like this, it means in this line, y value is decreasing, x value is increasing, right? Y value is decreasing, x value is increasing. That means slope will be what? Negative. If there is a line like this will have a positive slope. Horizontal line, zero slope. Vertical line, infinite slope. This is a basic concept, right? That means this line will definitely have a negative slope. Okay, this line definitely have a negative slope. Now what we do? This is your initial weight. New weight will be equals to what? Initial weight minus the slope. Okay, initial weight minus slope. Okay, that means weight minus some negative value. That means weight plus v. That means your next weight will be on the right hand side. You will touch over here. At this point, again there will be a new error value. Again you can have a slope of a tangent like this, right? Isn't it? And again you can calculate the same thing, and again you move towards right. So if you do this thing repeatedly, after some time you touch the minima where slope of the line, you will have a horizontal slope, and that will represent almost zero. Okay, you have a zero slope, and that's why this thing will not change anymore and your weights will not change. Okay, so this process will gradually take you to the minima from whichever side you start. If you are starting from here, then also it will take you to the minima. If you start from here, suppose this is your initial weight, okay, you don't know the actual optimized weight, so that's why you're starting from here. At this point there can be a possible slope of a tangent, right? So at this point of error, okay, when you calculate these things, that means you calculated the slope of the tangent, which will be positive. As it is positive, that means weight is equals to weight minus the current weight minus the slope. Okay, this is your formula we use, current weight minus slope. So it would be like this. Just a minute. This thing actually needs at least 2 times of explanation, right? So first time I already explained. Today when I'm explaining, so you I expect this will get clear. Okay, so here weight is equals to what formula we consider? This one. Okay, that means weight minus v. So you move towards left side because weight value is decreasing. You come over here, again there can be tangent possible, again same formula, and it will take you to the minima. When you touch minima, the weights will stop changing anymore, or it will change very small portion, and then we can say that yeah, we are at the minimum error level. Understood? Yeah, so this is what actually we discussed over here. If you go into this code also, okay, what I did here, we have a data. I want best fit line. So first I explain you through the least square method. Least square method is very easy. Error optimization is something that you need to understand. Here x and y is there, so we calculated the gradients. Okay, and after calculating the gradients, we are putting it over here, and that's why my error value decreased. Initial weight value that we considered over here, 2 and 1. That means if I consider this as x and this as y, I want best fit linear relationship between them. As I want best fit linear relationship between them, I calculated y hat using this equation. As I calculated the y hat using this equation, we have over here, we require w0 and w1. So w0 and w1 is used. Y hat is calculated. Once we have this thing, this is our error value. I want this error to minimize. Calculated the gradient and use this formula. What is this? This is called learning rate. Okay, what is learning rate? When we are operating like this, suppose my initial weight is 1, okay, and the gradient we are calculating, that is your differentiated value over, comes out to be 256. So next weight value will be what? 1 minus 256. Okay, so this will be minus 255. That means a big change. Okay, you change the weight value from 1 to minus 255. Okay, but to, kind of touch the minima, right? To go towards the minima and settle down at the minima, you required what? Baby steps. Okay, you can't take a very long step, you can't jump from here to there, right? So just to make sure you should take a baby step, what we do, we make the change like this: weight is equals to weight minus learning rate into, like this, where learning rate we can use like this. Let's say weight is equals to weight minus, let's say 0.001. Depending upon this value, the learning rate can be used. Okay, that means 1 minus 0.001 into 256, that is 1 minus 0.2, that is 0.8. Okay, so your weight will change, but it will change in a very a small portion so that you can converge easily. Okay, to converge you require baby steps, right? So that's why we take a learning rate which will scale down the value of gradient so that slowly you can optimize. So you can say my error from 4.8, it came down to 1.42. Done. So this process requires repetitive iterations, right? So that's why I put it in the loop, and then at the end our error stops changing, and here I have an absolute error, mean absolute error, which is very less, and these are our trained parameters. And then when we identified YH, now this YH or Y hat, okay, this YH or Y hat is being calculated like that. How? This one. Okay, so this is a linear, this will give me a linear line. If I plot between X and Y hat, I'll get a linear line, because this is the equation that is used. Okay, how YH is basically calculated, if you see, this is how YH are we calculating, right, which is a linear line. So at the end, if I plot X and YH, I'll get a linear line. So this is a best fit linear line. All right, next I took the actual data, right? In this data we have TV, radio, newspaper are the features, and sales is my target. But initially we are just considering only one feature, that is TV, okay, and Y is our sales, and we implemented the same process. Again error came down, and it came down to 10.79, which is mean squared error, and mean absolute error is 2.54. that is way lesser than that. Obviously squared and absolute error will be different, right? Because square you are penalizing the error mode. So that means if I want to use these trained parameters, okay, if I want to use these, where is trained parameters? Okay, if I want to use these trained parameters to predict the sales value, okay, if I want to use these trained parameters, which are the coefficients in intercept of this linear line, to predict the sales value, all right, I may expect an average error of 2.54. How can I predict? This is how I can predict. Okay, then we implemented it for multiple linear regression, in which we consider two features. If I consider two features, what will change? Nothing will change, only the equation will be for two components, x1 plus w2 into x2. Okay, this is for multiple variables, so it becomes multiple linear regression. So if I have two variables, then we have one, this is the first gradient, this is for w1, this is for w2. Okay, then again we optimize it, again error came down. So here more number of iterations actually required. I guess I had used 1000 iterations over here, most probably. Yeah, 1000. So my error came down. These are the trained parameters, and now my error came down to 1.24. That means when I use one feature, my error was 2.5. When I use two features, my error is 1.24. Okay, this is how we made the predictions. But this is just for knowledge, so that you should know what is going behind the scene. In actual data, with actual data or some actual problem statement, you are not going to write the code in this way. Okay, you have to write the script using the library. Okay, so that's why we are using scikit-learn over here. We have two things called features and labels, simple linear regression. Here we don't want to do much. First, once we have features and labels, x and y defined, what we do, we split the data in two parts. Okay, so that one part of the data we can use for training, another we can use just for test purpose. Okay, it's like hide it. Okay, like we just want to check how my model is going to perform on a information which is not used for training, right? What we want we want to check how our model is going to perform on a particular set of information which is not used in training, right? Like when you go for exam, okay, is it like same question asked which had been taught in the class? No, conceptually similar questions will be asked, right? So same thing over here, I want to check how is it performing on a data which is not used for training. So we are splitting it. The according to this line of code, 75% of the data will go to training and 25% will go to test. That's why train size 150 and test size just 50. Okay, then we import the algorithm and define the model. Then we train the model over here.
Voice is breaking for voice.
Okay, once the model got function error we are getting for the train data, and this is the error we are getting from the test data. Though both are close, as both are close, it means that we can expect similar level of performance on any new information. Okay. For any new information, how can we predict? Using predict function. Multiple linear regression, just pick two features, is split into two parts, train and test part, define the model, make the predictions, calculate the error. Okay, first calculate the difference. So what we had seen now yet, like how by selecting the different features, how our error value actually tuned. Sorry, we just faced a little bit network disturbance. I don't know it was a network disturbance or what, but now I guess it is more stable. Recording fine. So now we have this particular data. Though, how do we start? See, whenever we have a data, we first try to check the data types, right? So here, if I check the data types, df.data types, so I find that all of them are numerical value. I'll check what the null values. Do we have any null values? We don't have any null values. Everything is quite fine. Okay, so there is data irregularities, or you can say data quality issues are not there. Okay, so if data quality issues now are not there, what we do here? We'll go ahead and try to check the correlation. Okay, this correlation helps us to understand what are the features which are important for our model. Okay, so we can make this thing looks more visually better by using Seaborn library. Import Seaborn as SNS. Okay, SNS dot pair plot. Okay, SNS dot heat map. Okay, and then I'll do what? Annotation is equals to true, and I can use format is equals to 0.2f. Okay, so it shows that this orange color is showing a kind of, I can also use over here color map. This already I told you, in red, yellow and green. Okay, so it's highly green means it is kind of a very important thing, right? Like for the sales, okay, this is a sales thing, right? So for the sales, okay, the TB component is kind of a highly influencing it, highly correlated. This is next one. This is in red, which is very least correlated. It means newspaper may not play a very important role while predicting the sales value, or we can say that newspaper is not affecting the sales much. And same thing we had seen in our last example. When I added the newspaper in the training process, okay, my model performance didn't improve. It remains same compared to the previous performance. All right. Okay, so here we get the understanding. So it means that with the TB and radio, we can get a better model, right? So already we did it. Let me just copy and paste it from here. Okay, one more thing that you can do apart from this heat map, you can also try for pair plot. SNS dot pair plot. Okay, df, right? So if you go for the pair plot, you get a kind of a plot, graphical plot, that will help you to understand the relation, right? So if you see the relation of sales with respect to, okay, the relation of sales with respect to TV is having some pattern. Radio is also having a pattern for most of the data, right? More than 50% of the data is having a pattern, but in case of newspaper there is no specific pattern. Okay, that's why newspaper is something which is not affecting the sales much. Like for lower expense we have lower sales as well as higher sales. Okay, so this also makes sense that newspaper is not a very important entity for it. Okay, so now we already build a model like this. Let me just make it now model A. Okay, this model is using two important components from our data. What are those two important components? TB and radio. Okay, why? Because newspaper is not very important as per the last class discussion and as per the current correlation analysis. Okay, so now when I build it, I got an average error of 1 point close to 3. Now question is, how can I improve this performance? Okay, so there are multiple ways of improving the performance. Okay, see, we check whether the target variable is normal distributed or not. So this is already normally distributed, so we need not to worry about it. Okay, it is already normally distributed. Second, what can we do? We can go ahead for the non-linearity. Okay, so let's go ahead and break this linearity so that we can check. So what is non-linearity? See, if I talk about these two features, then what linear regression is doing? Linear regression is working or using this particular equation. All right, linear equation is using this equation. Fair enough. What non-linear will do? Non-linear will depends upon degree of equation. Okay, let's say it is 2. So for 2, the non-linear, okay, if this is your linear equation, then this can be converted into non-linear like this: x1 plus w2 x1 square. Okay, y hat is equals to w naught plus w1 x1 plus w2 x1 square plus w3 x1 cube. It is what? Non-degree. Sorry, non-linear. This is non-linear for degree 2. Okay, this is degree 2 non-linear. Okay, this is what? Degree 3 non-linear. All right, isn't it? Now here, if I use y hat is equals to w naught plus w1 x1 plus w2 x2 for two features. Okay, this is a linearity for two features. So non-linear can be y hat is equals to w naught plus w1 x1 plus w2 x2 plus w1 x1 square plus w2 x1 into x2 plus w3 into x2 into square, w1 w2 w3 w4 and w5. Okay, so what non-linearity is doing? Non-linearity is actually increasing the number of weights, isn't it? In the linear process, we have, if I am having one feature, then I can have one coefficient and one intercept. Okay, if I have two features, then I can have two intercepts, sorry, two coefficients and one intercept. Okay, that is limited. But when I move to non-linearity, okay, when I choose non-linearity, what change happened? Now with just one feature, I can have two coefficients and one intercept, or I can also have three coefficients and one intercept. Okay, when I have two features, how many coefficients I can have? 5. and one weight, one bias or intercept. That means what are we increasing by breaking the linearity? We are increasing the number of weights. That means we are increasing what? Number of trainable parameters. Okay, we are increasing the number of trainable parameters for our model. Okay, initially our model was having limitations of have only 2 or 3 trainable parameters, but now it can have 5, 6, 7, 10 trainable parameters based upon degree of non-linearity. Am I clear?
Yes, but I just wanted to ask you how did you, sir, write the formula? How did the weights increase? Number of weights increase? There are two coefficients. Then you also wrote three other.
I'll explain.
What's
Understood.
the
Got your
formula?
question. Got your question. Got your question. See, like when I was using the linearity, what was happening? Using this formula, our y hat was calculated, right? This y hat was calculated using this formula, right? And thereafter error was calculated, right? And
Yes, yes.
thereafter error optimization happens to minimize the error. All right. Now, in case of non-linearity, what happened? Here also your y hat will be calculated. Okay. Here also we have to calculate the y hat, but the formula will, if this was for the linearity, for linear regression. Okay, this was for linear regression. So for non-linear regression, I will write it like this: W2 x1 square. So I added a square. Now this equation becomes non-linear. It can't remain in a straight line. Okay. So it's like here, this is a formula for linear line. Okay. And this is a formula for non-linear line. All right. That means if suppose you had been X given, okay, let's say that was your year of experience. Okay. And you have over here Y given. Let's say this is your salary. Okay. So year of experience, let's say 5, 7, 3, 2, 1, like that. Okay. And salary, let's say 50,000, no, 40,000, 30,000, okay, 60,000, 20,000, like this. All right. Now, what will happen? Using this equation, okay, using this value, if you calculate the y hat, so you can easily calculate. Suppose you can just calculate it like this over here. Okay. In case of linearity, you required what? You required only these two things. Let's say these both are 1. So y hat will be equals to what? 1 plus 1 into 5, that will be equals to 6. Right? And if you use it over here, so this is W0, W1 and W2. Now we have 3 things that you have to decide. Let I decide all of them as 1. So the value will be what? 1 plus 1 into 5 plus 1 into 5 into 5, 25. That would be equals to what? 25 plus 5, 30 plus 1, 31. Okay. Now what is the difference between these two? Because both the time I am calculating the same, I am calculating one important entity, y hat. Okay. This is y hat linear and this is y hat non-linear. Okay. So y hat linear had given me 6, y hat non-linear had given me 31. All right. So if I am using linear regression, then this will be considered as error. Okay. And if I am using non-linear regression, then error will be equals to what? Y minus y hat non-linear. This is y hat non-linear. Okay. This is our error value. And once I have the error value, I have to optimize the error. Now for optimization of the error, you have to actually tune 3 trainable parameters. Okay, in linearity you are tuning only 2 trainable parameters. Now you will tune 3 trainable parameters because you are using degree 2. Are you getting it? That means here, before using this particular non-linear regression, you have to transform your data. Okay, if this is your data given, so you have to create one more data column over here, which is called x square. 25, 49, 9, 4, 1, like this. Okay, if you are using degree 2, if you are using degree 3, then you require x cube as well. 125 you can calculate over here, 27, 8, 1. Okay, right? So if you are using degree 1, only this equation will be your feature. If you are using degree 2, then these 2 will be your feature. If you are using degree 3, then these 3 will be your feature. Is it getting clear?
Yes.
Okay, let's go for the practical understanding so that we can get it better, right? Oh, what happened? So let's say I have to understand over here non-linear regression. Okay, so for non-linear regression, what I need to do? Let's say x is equals to, okay, let me use x1 is equals to np dot array 3, 5, 2, 7, 9. Okay, then y1 is equals to np dot array, okay, 4, 6, 3, 8, 7. Okay, like this. Now I'll plot it. Plt dot scatter x1 comma y1. Okay, then plt dot show. Okay, plt is not defined. Okay, so let me just import it first. Import matplotlib dot pyplot as plt. Import numpy as np. Okay, so it is what we have right now. If I'm using linearity, okay, so what will happen? Okay, first let's try to build the linearity over here. Linearity already you know, it will take hardly 2 minutes, right? So I need a library call from sklearn dot linear model import linear regression. Define a model linear is equals to what? Linear regression. Okay, then model linear dot fit x1 and y1 is there, right? So I'll just use x1 comma y1. Okay, so now it is saying that you require 2-dimensional data. No problem, just let it be 2-dimensional dot reshape 5 cross 1. Okay, so now it worked. Now as it worked, so I can do what? I can use yp1 is equals to what? Model dot predict x1. So now I'll have the yp1 calculated, model linear is there. Okay, so based upon this model linear, if I'll try to plot it once again, okay, I should not use this guy. Okay, here I will use what? Plt dot plot. Okay, what? x1 comma yp1. Okay, so x1 and y1 is random data distributed, but yp1 is linearly related. So I get a best fit line over here. Obviously, this is your linear line. Okay, so I did it for comparison. Okay, now let's go ahead with the non-linearity, right? So for the non-linearity, what do we do? we are already having the x1 like this, right? Now what happened here? I have to decide the degree, right? 1 degree, 2 degree, or something like that, right? So let's go ahead with the 1 degree, right? So we will do what? From sklearn dot pre-processing import polynomial features. Okay, so this is an inbuilt library which will take care of data transformation. Okay, we want to transform it into 2 degree, right? So now here I will do what? POL is equals to polynomial features. Okay, and then I will do what? I have to define, this is the object of polynomial features, so I have to define degree is equals to 2. Okay, and then we do what? We fit the data. POL dot fit. This is the first data transformation exercise we are doing. Okay, this is what? Data transformation. All right. So now if I execute it, anything happen? No, it will not happen. Okay, because fit will do what? Fit will not transform the data. Okay, last time when we use fit, we use for training. Okay, so when we have a algorithm and we are using fit, okay, it basically trained your model. Okay, when we have a algorithm and we are using fit, okay, it will train your model. But here we have a pre-processing library. What do we have? We have a pre-processing library. So here after fit I have to use dot transform x1. Okay, so what we got? Let's just look at this thing very carefully. I want 2 degree transformation because I want 2 degree non-linear regression. So my data is transformed like this. Y for this equation, y is equal to w naught plus w1 x1 plus w2 x1 square, right? So here I have 1, okay, here I have x1, that is 3, here I have 9. Okay, because these things your model will find out during error optimization. All right, now again for the next data, it is 1, it is 5, it is 25. Okay, 1, 2 and 4, 1, 7 and 49, 1, 9 and 81. So what it is doing? It has transformed your data suitable for non-linear equation so that you can use it for the regression purpose. Okay, so as first column is all 1, we don't need it. Okay, first column is all same. If something is all same in all the data sample, that is not a very important thing. So I can do what? I can use over here include bias is equals to false. What it means? I don't want to include the bias value. Okay, so now my training data is changed. Okay, it is not x1. Now my training data will be what? X1 polynomial. This is my new training data to train my model. Am I clear? Okay, that means if I use the same process that we used earlier, okay, here I have to use what? I can't use x1. I have to use, everything will remain same, but just here the data will change for training. Okay, that means here it's not like that we have any other library. No, we don't have any other library. Library is same. Okay, only what are we doing? We are basically using over here transform data, right? Because once you put over here a data like this, w0 plus w1 into 3 plus w2 into 9, right? Now linear regression library can find out your coefficients, right? Isn't it? You are passing what? You are passing the, you're not passing over here x, only x, you are passing x and s square both. Okay, so actually here the data for the training we are changing. Okay. So as the data for prediction will also change. Okay. Now for plotting, actually only 2 dimensions, so we can plot it like this. That is fine. That is not a problem. Okay, because x1 only, x1 and yp1 are now non-linearly related. So let's see what happened. Okay, so now it is trying to be non-linear. Okay, but this is up and down. The reason being it is not sorted, isn't it? We can also sort it, like say to do this thing, let me just have a data define x underscore new is equals to np dot line space. I am taking a sorry. I am taking a data in a actual sequence. Okay, from minimum value, that is 2, to the maximum value, that is 9. Okay, equally spaced data I am taking. Okay, between 2 to 9, and thereafter I'll transform it. X new polynomial will be equals to what? Polynomial dot transform x new. Okay, and then the prediction I'll make on this particular data, because this is in a one sequence increasing order. As it is in increasing order, so my line will be non-linear, but it will not be zigzag. X new and yp1, that's fine. Oh, reshaping is required. Huh? Where is reshaping required? Here. Okay, so dot reshape -1, 1. Okay, so you can say how the linearity we are going to the non-linear case. So when I am going to for the non-linearity, what exactly happened? The line is trying to be more aggressive, okay, to fit into your data, right? So what I did here, the training was made on what? Non-linear data. Okay, I generated some new data points between 2 to 9. Okay, reshape -1, it's like I don't know how many data points are there, that's why I use -1. Okay, what I mean, let's say if I have a data points like this, in case you don't know it. Okay, so these are our equally spaced value between 0 to 9, but this is one dimension. To convert into 2 dimension, I should know that how many values are there, like 1, 2, 3, 4, 5. I have to count it. If I don't want to count, just use dot reshape -1, 1. Okay, so now it is what? One, it's like it will be converted into single column data, and which is 2 dimension. -1 will represent, automatically it will be replaced by number of rows. So same thing we did, and then on that data I used to transform polynomially and make the prediction, and then plotted x and yp1. Okay, why I am not using x1? Because x1 was not kind of a, it is not sorted. Okay, it is just increasing and decreasing. So as it will increase and decrease, so your plot may be like this, right? So if I sort it, I'll get a better kind of a curve, which helps us to understand that now we are not working on linear things. Okay, if I will use 2 degree, here I use 2 degree. Can we use 3 degree? Yes, we can use 3 degree also. Let's try. Okay, here I'll use 3 degree. So as I use 3 degree, so let's say I use x1 pol 3. So what I get? X square x cube, right? That means now for the training, we are planning to use this 3-degree data. Which 3-degree? This 3-degree thing, right? Okay. Target will remain as it is, no change. Okay, rest. Created a new data, sorted. This new data get transformed for 3-degree equation. This new data get transformed for 3-degree equation. Predicted on new data, then plotted, right? So let's see. So when it becomes 3-degree, it is trying to be more aggressive, right? Trying to fit your all the given points. Am I clear? Let's take one example over here. I am sharing this data file with you. I'll also work on it. Salary data set. Okay. Compare linear and non-linear regression. Okay. So it's like df salary is equals to pd dot read csv df salary dot head. Okay, so this column is not required. So index underscore column is equals to 0. Right, so we have two entity over here. One is called x. Let's say x is equals to what? Year of experience. Okay, and y is equals to what? Salary. plt dot scatter okay, so now just try to implement both linear and non-linear, okay, and check the model performance.
Bipul, one quick question. On the DF salary, not this one, DF salary, I see two brackets, right? But for for Y it's only one. For X it's two brackets, and for Y,
Okay.
why is
Okay.
that? No.
Okay, see, actually, why I did it? Because we are using the sklearn library, right? So sklearn library is planned, like we are picking linear regression, okay, from sklearn, right? So now this will help us in creating a model, okay.
Got it.
So now every time you can't use a single feature. We also use 2 features, 3 features, 4 features, right?
Right.
So when you are going to pick 2 or more than 2 features, you have to always use 2 brackets, right?
Okay, got it.
Okay, like if you are going to pick like 3 features or 4 features or 2 features, you have to use 2 brackets.
Right.
All right. So this library is being created to help you creating a model either with 1 feature or 2 features or 3 features.
Okay.
Right. That's why when you are taking the 1 feature, then also you require 2 bracket, right? Because they can't create different libraries. Okay, they can't create a different like one library for single feature, the library for 2
Got it.
features. No, right?
Got it.
So it should be there should be a single library which can help everyone,
Got
right? So it's like if you're using single feature, you can use two bracket, and single feature you can also access using single bracket. Okay, that will also work.
Okay.
Okay, but when you go for more than two features or two or more than two features, single
Yeah.
bracket will not work.
No, it will not work. Correct. Got it.
Yeah, so that's why if you are creating all the program manually, then it is not required.
Okay.
You can go with a single bracket, but since you are using library, so for the library we have to use this two-dimensional data.
Okay. Thank you. So people, we can use the scikit-learn for creating the model, right?
Right.
Okay.
See what happened with the non-linearity exactly. The non-linearity is like you transform the data first. Okay, so when you transform the data as x square x cube, now the algorithm will use your transform data. Earlier linearity, it was using, let's say, only one component. Okay, but in non-linearity it will use multiple components. So for each component it will try to find out the coefficients.
Correct.
Right, so it's like number of trainable parameters increased. Okay, that's why we expect a better model performance compared to linearity. Okay, that means actually you are increasing the size of the model. Okay, if this is a size of linear model, then this is a size of 2-degree non-linear model, this is a size of 3-degree non-linear. So size represents what? Number of coefficients.
Right.
Okay, more coefficients, larger size, less coefficient, a smaller size. Okay, so in this case, if I have to use linearity, what will happen? Here I have a data, right? I can do what? I can just split into two parts from sklearn dot model selection import train test split. Okay, x train, x test, y train, and y test. That would be equals to what? Splitting it into two parts, x comma y. Okay, next what we can do? We can use from sklearn dot linear model import linear regression. So model linear salary. That would be equals to what? Linear regression. Okay. Thereafter, model linear salary dot fit. What? X train comma y train.
Right.
Done. And then I can make the predictions. Model linear salary dot predict what? X train. So this is a predicted value, y train predicted. Okay, done. Now I can just have the predict for the test data as well. So here let me just write the comment, split into train and test. Okay, thereafter import suitable algorithm to train, then define a model to be trained. Okay, thereafter make the predictions using the trained model. Okay, so this is a prediction made on training data, then we can have a prediction on the test data. So y test model linear salary X test. This is just a linear model, and then we can evaluate the performance. We can check mean absolute error for the train. That would be equals to what? Absolute value of the difference between Y train minus the predicted value dot mean. Okay, and MAE test, that would be equals to what? Y test minus Y test predicted dot mean. So TRAIN. Okay, so Y train minus Y train predicted, Y test minus Y test predicted. All right, now I can print over here train mean absolute error, MAE train, and then train test mean absolute error, MAE test. Okay, getting some error over here. Why I'm getting error? X train X test, Y train Y test, right? So model linear salary dot predict X train. Okay. A spelling mistake. This is coming out to be close to 4,200 or something like that, right? Between 4 to 6,000. Now I'll just try to plot it X train, comma Y train. Okay, and linear line can be plotted as PLT dot plot X train, comma the predicted value, right? Okay, which can be red in color. All right, so this is about the linearity. Okay, now let's try to break the linearity. For breaking the linearity, what we have to do? Same process. First pick the X and Y. Okay, now we have to do what? From sklearn dot pre-processing import what? Polynomial features. Now POL is equals to what? Your polynomial features of degree 2. Okay, 2 degree, right? Okay, so same thing that we did here, and we can also use include bias because I don't want the first column as 1 1 1 1 1, right? So include bias is equals to what? False. Now I can do what? POL dot fit. So when I fit it, what will happen? Your process comes to know that how many features are there. That means this algorithm comes to know how many features are there. And then we do what? POL dot transform. Okay, X. So what we got? X, and this is X square. Okay, so this is your X polynomial. So we have created a polynomially transformed data. Okay, so now we did what? Polynomial regression. We created a polynomial transformed data. So by default, X was of shape only one features. Now X pol is of shape what? 2 features. Okay, it's like 1 is transformed to 2. X and X square. Next, I'll copy this whole thing and paste it over here. Okay, so splitting. So now splitting will not be done on X. Now it will be done through X pol. Okay, we'll just create a train test split using polynomial features. Fair enough? Model is defined. Let me just use non-linear over here. Okay. Name only I'm changing. All right. White train predict non-linear. This is also non-linear. Okay. Rest everything is fine. So let's check what happened. My error value came down. Yeah, somewhat came down. Earlier it was 4120 and test was higher, but now for test also it came down. Okay. All right. Now let's try to plot it. So for plotting PLT dot scatter X train comma Y train. PLT dot so. Okay. Oh no, what happened? Okay, now it is not plotting because X train is of, see, this is something that we need to check. X train is not having a single column, it is having two columns. So I need to define over here which column I want to use. Obviously the first column I'll use because the first column is the actual data column. Okay, the second column is what? Is X square. So I got the scatter plot. Now I need what? The line plot. So PLT dot plot, this will remain as it is. Okay, and then how we calculated the output? This is how we're calculating the output. Okay, so the relation between X train and Y train predicted is non-linear. So that's why we can say we're getting over here non-linear thing. Okay, now we can make it better, that means more smooth. If I take a data over here, let's say what is the minimum and maximum value of this guy. I'll take over here np dot line space, okay, with the minimum value and maximum value. Okay, how many? Let's say 10 values I want. Okay, so this is what new X. Okay, so if I have new X, what I can do, I want a prediction on this. So if I want a prediction on this, I have to transform it into non-linear form. Okay, so how can I transform? I already have the object which can transform. So I'll take this thing, put it over here, pol dot transform, okay, new X. Will it work? No, it will not work because this is one dimensional. So I have to reshape it -1, 1. Sorry, reshape I have to do outside of it, right? After transforming. Oh, it's transform, not transform. I'm doing. Okay, so now it is, see, we have a polynomial transform data. That means this is new X polynomially transformed. Okay, why are we using it? Because this is sorted. As it is sorted, so using this, if I'll try to make the prediction, okay, and then that output I'll try to plot, right, I'll get a more smooth curve. Okay, so now using this I have to make a prediction. How can I make a prediction? I already have a model. Okay, dot what? Predict. What can I feed? This new set of data. Okay, prediction is there, so I can just write over here new Y pred. All right. So everything is done. What I do on the x-axis, I will feed this new x, and on y-axis, I will feed this predicted value. So you can see this is a curve like this. Okay. So this is about the degree 2. Okay. Can we go for degree 3? Let's try for degree 3. Only I have to add it over 3. Okay. That's it. Error value you can see coming down, right? Here predicted. Okay. Trying to be more aggressive, right? If I use degree 4, so what can we do? Okay, how much degree can we increase? 4, 5, 6. See, there is no limit of it. Okay, we have to take care of the things like how efficient our system is, and second, after some time your model will start getting overfit. Okay, see, now only train error will be decreasing. Okay, let me use degree 5. With the degree 5, you can see when I use over here degree 5, okay, you can see only this guy is decreasing. Okay, if I use degree 6, that means model is getting well fitted on the known data. Okay, now test also decreases over here. Okay, so let me check. If train and test both are decreasing, then it's fine. Okay, degree 7, but again, if you are using, if you're increasing this thing, what are we increasing? You are actually increasing the size of your data. Okay, that means the processing time for your model will get slower, right? So as of now, what I can see, that my model performance is not changing much. It is almost very close to 4000. So there is no point of making it 6 or 7. Even this level of performance I was also getting on degree 2. Okay, so if the performance is not improving, there is no point of increasing this thing. Okay, or you can use degree 3 maximum over here, that's fine. So you have to compare the performance on changing the thing. Okay, so what we did over here, we just transformed your data for 3-degree equation, and that data we are using over here to split. This is data we are using over here to split, and then that one we are using for the training. That's why when my model is predicting, it requires a non-linear data for the predictions. Okay, that's why when I have new set of data, we converted into it the 3-degree form. Okay, and then we are using it for the predictions, and then we plotted it. All right. So if you got little bit of idea that how is it working, next I'll give you 5 minutes of time. Just try to apply the non-linearity in your advertising data. Please go through it. Whatever the questions you have, you can let me know. Right? Apply non-linear regression on advertising data. Okay, that's why I took these data. Like it was not difficult for me to take some very fascinating data and start working on that. Okay, and let you build some kind of a model. But I want your fundamentally you should be good, so that later on optimization you can do better. Okay, you should know whether to apply, where to apply linear, where to apply non-linear. Okay, these all kind of concepts, if you know, you can build your model better, right? There is one thing called building a model. Okay, building a predictive model, and there is something called building a good predictive model. So we have to build a good predictive model, right? We don't have to just import the library and use it. So please try to implement non-linear regression on the advertising data, and let me know that what is your approach. Please think of it. Non-linearity using one feature. Okay, like suppose x is equals to TB and y is equal to sales. Okay, and apply 2 degree. Okay, and check what is the average error, because with linearity our average error was 2.5. With the linearity our average error was 2.5. So with the non-linearity, please check the average error. Next step, we will take what? 2 features. Okay, we'll not take 3 features because 3 features are not important. The third one is not important one. So we'll take two features, and thereafter we'll again apply the non-linearity. But first finish this thing. Thereafter I will work on this thing. See, you need to do what? Just take one of the data columns, like that's I am taking over df of TV. Okay, and y is equals to df of sales. Okay, now we are planning for what? For non-linearity, right? So non-linearity means what? We have to check, we have to decide 2 degree, 3 degree, 4 degree what. See, generally we use 2 or 3 degree. Why? Because if you go beyond 2 or 3 degree, you are increasing the data size too much, so process will get very slow. Okay, that is one problem. And second problem, your model may be overfit. All right, so here, so from sklearn dot pre-processing import what? Polynomial features. Now POL is equals to what? Polynomial features. Okay, what we define here? Degree. Okay, let's say 2. Okay, then what we do? We'll let this component know about what we want to transform. We want to transform x. So POL dot fit. What will fit? X. So now it has the information that okay, there is one component that needs to be transformed, right? So POL dot transform. Okay, x. So we get it. So in this thing, the first column is all 1. We don't require it. So what we do, we'll use over here include bias is equals to false. Okay. So now we don't have the first, sorry, include. Oh, when I'm doing it, it should be in the fit, right? Oh, I guess my mind is not working today. Okay, so actually when we define object, then we should define all the properties. I'm putting into fit, then transform, sorry. So see, whether you have to define the degree, whether you have to define the include bias, everything should be defined with the object, because that object will have the method and that method will work according to the parameters you defined here. Okay, so I want 2 degree and biasing I don't want, that means I don't want 1 1 1 1 1, right over there, right? So now I have polynomial features like this, x polynomial, right? So our TB component now we are transforming into 2 components. If you see earlier it was just 1 component, now we have 2 component, right? If you check it, what? X underscore Paul, it is having x and x square. Okay, the first column is x and second column is what? X square, right? Fine. Now what we can do, we can have the x and x test, right? So from sklearn dot linear model import linear regression, right? So here I can define model linear advertisement, sorry, non-linear, right?
Non-linear.
Model non-linear. Okay, before that we also need to split it, right? From sklearn dot model selection import train test split x train x test y train and y test. Okay, x underscore pole comma y. Okay, so now splitting will be done, and thereafter we'll fit the data.
Bipul, one doubt that I have is, so we are doing X train, X test, Y train, Y test, and you are splitting it.
Mhm.
Train test split great, and then you're saying X pole. Uh, why X pole? Because that's the number that we're using. Uh,
Okay,
so
see,
yeah,
if I want to use linear regression, okay,
okay,
so I will use this thing x.
correct,
Okay, but I want to use non-linear. That means I
correct,
want the component x and x square both.
correct, correct.
Okay, so that x and x square component is being generated using this guy,
Got it, got it.
right? So if you see over here x pole, okay, it is having two components, one x, other x square, right?
Got it.
Okay, so since we have to use both of them, right,
Mhm.
that's why what are you doing, we are splitting x pole.
Correct.
Okay,
And then here you're writing X train. Now X train is a command, right? Like
x pole is over here, and y, this one is splitted into two parts. Okay, x train and x test, right?
okay,
75% data is in x train and 25% is in x test.
got
Okay,
it, got it.
and this guy is split it in two parts, y train and
Okay,
y
so,
test.
so X train, X train will contain X pole, right?
Yeah, x train will contain 75% of x pole.
Got it, got it.
Yeah, okay, because we need polynomial transform data, that's why. Okay, if you see over here, what is the shape of x pole? It is 200, right? Cross 2.
Correct.
Okay, we have, because x and x square, right?
Got it.
Okay, so now if we are kind of creating over here x train, so x train is having those two components, but only 75% of the data, right?
Got it. Got it.
Okay,
Yeah.
so we are now training on x train. That means we are now training on the polynomially transformed data, right?
Right. Like people just in normal, the coding parlance, like, what is X train? Is it an object?
Variable.
It's a variable. Like I just wanted to understand, like we will always have to use X train as the variable name, right? Like we cannot use anything
No,
else.
you can use anything. It just kind of it is easy to recognize, right?
Got
Okay,
it.
that
No,
this
okay,
is
that's what I wanted to understand. Okay, all right.
right,
Okay.
right, right. It is just easy to recognize that this part of X data or this part of feature we are
Got
going to use for training, and
Okay.
this part of feature we are going to use for only testing
Okay,
purpose.
okay, got it. Okay, I think I was confused there. Okay.
Mhm.
And why
Okay.
do we write bias is equals to false, and why are we not reshaping it? Just like you in the previous slides, you
Mhm.
were mentioning reshape -1 into one, -1 comma one, and this bias bias is equals to false, right? So, what's the what's the meaning of that?
Okay, I'll tell you. See, bias equal to false means what? If I'll not use it, right? Let's say I'll not use it, right? See, here better I should explain with a simple one because it will be easier to understand. Okay. Okay. So see, this is our salary data, right? Now we did what? We defined 3 degree. Okay. And I'll not use it. Okay. That means this process will give me what? This process will give me x, x square, and x cube, because I want 3 degree transformation, right? isn't it?
Right, of course.
Data will be transformed into this form. Okay, once this thing will execute, right? So let's check what happened. Okay, we got over here not 3, we got 4 components. Okay, to make it to understand better, let it be used 2. So I was using over here this 2. So I was expecting x and s square. So I'm getting x and s square, but along with that I'm getting 1 over here. Okay, so all the sample is having 1 1 1 1 1. So this component is not going to be very important for machine learning purpose. Okay, because all the features are same
And
for
why is
all
this
the
one?
samples.
And why is this one coming? Okay. So the one is your intercept, and x and xy is a coefficient. That is why one
Right,
is
right.
the
Yeah.
coefficient.
Why it is coming? It is coming because of this reason. Because your actual equation
Exactly.
looks like this.
Right.
Okay. It is your actual equation, right? So in this equation, this x square. Sorry, I made a mistake. In this equation, this is x1, this is x1 square. So that is coming over here. Okay. But here also 1 is present, right?
Of course.
Isn't it? Okay, so because of this it is giving me 1, right? But if I will not use it in the data, then also my algorithm will give me the intercept calculated. Okay, w naught will anyhow will be calculated. Okay, even I will give this one or I will not give this one, w naught will be definitely calculated, right?
Okay, but if the value is different other than 1, then it will be different.
No, see, how it can be different. It's a for the first guy, like for this particular thing, it is what? It is a value which is called bias. Okay, that means when all the features are 0, then whatever the value of y that will be, whatever the value of y will have, that is represented by this guy, right? So this will always be there, and for this guy, this one will always be 1.
Okay.
Okay, this is always 1, right? It is like this. Okay, so and for other one it is like x1 into w1. Okay, for it is x2 into w2. Okay, but for the first one it is always 1. It is not like different. If suppose if it is other than 1, if it is other than 1, then it will be represented by other coefficients. Okay, the next value in the equation. Okay, like like suppose if just consider it at a very simple step. If suppose I say that no, this is not 1, this is something different. Okay, like this, w1 into x1 kind of thing, right? Now if it is something different, then it can't represent your intercept. Okay, suppose your intercept coming out to be over here 3, right? So instead of 3 it will make it 6, right? Okay, so this thing can't be more than 1, it will be always 1. The first component in the equation is always 1. Okay, see, even if I don't remove it, then also it will not be a problem. Okay, what will happen, I'll show you. Let's say if I'll keep it as it is, right? Okay, and thereafter when we build up the model, okay, model is built up. Now if I will read the model over here, model non-linear dot coefficient. Okay, I'll read the coefficient. So automatically it had given 0 to the first value, that is 1. Okay, 0 means what? 0 means this guy had been given a 0 weightage. Okay, that means it becomes 0 cross 1 plus what? What is the next value? Whatever it is, what is the next value? 10217 and this one, right?
Yeah, so that has no significance.
Right. So if I'll do it, it is like this. 10 whatever you can consider, it's like 102 whatever, right? Multiplied by 223 multiplied 10.6 plus minus something 4200 something like that. Okay, multiplied by 112. Okay, so this thing becomes insignificance, right? Because of zero coefficient, right? And if you check the intercept, so intercept is anyhow we are getting, right? This is actually the W naught value. Okay, the output that you get it over here, this is actually W naught. This is W1, this is W2. That one is not adding any kind of value to your whole process.
Okay.
All right.
Okay.
Okay.
And I just want to know that in which circumstance we use non-linear and linear. I mean, when do we know that we have to use this and that?
See, you have to actually apply and check. Okay, this is a tuning process. Okay, by just looking at the data, you can't decide. Okay, you have to apply linear, you have to apply non-linear, you have to apply reach, you have to apply lasso, you have to apply decision tree. Different things you apply, and then you evaluate all the
Error.
process, all the performance, and based upon the multiple performance
Got it.
accuracy and error, we decide which one is good, and whichever is good, that we finally deploy.
Okay, understood, understood. Okay, so I mean we apply, so instead of just putting one in the model, we will put linear regression, polynomial features, and we'll SVV, sorry, SVM and everything, lasso and everything, and then we'll find out the mean squared error, the R2 square error, the
Correct.
calculation and everything, and then we'll find out which is the least. If
Correct.
the least error we are getting, so we'll pick up that model.
Right,
that
right.
Right.
Correct.
Okay, got it.
All right. So here now, is it clear like what Xpol is doing over here?
Yes.
Okay. So now we have fit the data. So now we train this particular model using the non-linear transform data, because now Xtrain is being generated from Xpol. And what is Xpol? Xpol is a polynomially transformed data of X. Okay. So it is like creating training data from polynomially transformed data. Okay, so this is what we have, right? Now it is trained. Now as it is trained, we'll try to make the predictions. Okay, so y train pred, let's say that would be equals to what? Dot predict, right? Okay, that is what X train. Okay, this is what y test predict. Model non-linear advertiser dot predict X test. Okay, once we have both the things, I can do what? I can calculate average error, mean absolute error for the train. That would be equals to what? Your real value, minus the predicted value. Okay, and then we take the mean of it. Okay, MAE test, that would be equals to what? Your real value minus the predicted value. Okay, so now we have a print mean absolute error train. Mean absolute error test. All right. So is it coming down? It is not coming down, right? It's not decreasing. So here non-linearity is not making any sense. All right, let's try with 3 degree. Okay, it is making no sense. Like we are trying to apply the non-linearity. We can also check it over here. Let's say I will use x new is equals to np dot line space. Okay, equally spaced value between x train index 0, that is the first column is your actual value, because first column is x, next column is x square, next column is x cube. Okay, so the first column I am taking dot minimum to the maximum. So between minimum and maximum value of x train I am generating, let's say suppose 10 data points. Let's say x underscore new in a ascending order. Now all these data points I will transform into polynomially. I'll do the polynomial transform. So POL dot transform. Why I am using POL dot transform? I'm using POL dot transform because here POL actually knows the things like in which degree I have to transform. Okay. Now I'll do what? I'll use over here POL dot transform. But it is not working. Now here the answer of your second question. Why when we do the reshaping minus 1 cross 1, and why are we not doing here? See, when we did it, here we did it, here we are not doing. Why we are not doing? Because it is already a 2-dimensional data, right? It is already a 2-dimensional data. We don't need it. It is already a 2-dimensional data in a single column. But here we need to do it, because here if you check x new, okay, what is x new here? This x new is a single dimensional data. So POL, the object of polynomial transformation, can transform your data into 2-dimensional, can convert this guy into 2-dimensional like this. First one is 5.4, second one is also 5. What happened? Oh. Okay, so first one is over here 5.4, second one is let's say 37.73, 70.06, 102.4, right? So this information can be transformed like this, right? You know, we have to just arrange this one like this, then only it can be given to POL. Okay, because POL is an object which can transform into x square and x cube, okay, according to current state. Okay, because you are using 3 degree, right? Isn't it? It can do convert, but for converting also it requires 2-dimensional data first. Why it requires 2-dimensional data? Because initially we had used 2-dimensional data over here. Okay, we had used 2-dimensional already, right? So later on in the fit, whatever the dimension you are using fit, it will use same thing. So that's why here we required reshaping. So in the reshaping, first we pass what? Number of rows. We are not so sure about number of rows, so just use -1. It will automatically count the number of values, and that means number of rows will be there. All right. Now this information will be used for transforming. Why we didn't use earlier? Can you answer me? Because earlier data was already 2-dimensional. Here why are we using? Because here we have created a new data which is 1-dimensional, and that's why we are using it. All right. So now we have a x new polynomial. Now this thing can be used for making the predictions. So let's have our model. Dot predict X new pole, sorry. We have a predicted value. Let's say I'll make it Y new polynomial. So why I did it? I did it so that if I want to plot plt dot scatter, okay, what I want to scatter, let's say x train, the first column of our x train, because next column is x square and then x cube, with respect to y train plt dot so. I want to see the relation over here. So relation I can just plot using the line plt dot plot, okay, x new that we just created and the predicted value, which is non-linearly connected. Okay. So when I use single feature, the non-linearity is not helping me anyhow. So as you asked one thing, like when to decide whether non-linearity we have to use. So here non-linearity is not required because my error value is not coming down. All right. Okay. So just have a look. Okay. And then we need to understand non-linearity or polynomial regression on multiple features. Okay, what it means? Now we are planning to use two features at the same time. Okay, and then we'll apply the non-linearity and check what happened. Okay, so using two features, we already had seen multiple linear regression. Now we'll go for what? Multiple non-linear regression. All right. Okay, so for the two components, what happens? See, when I have only one component, okay, like x, we transform into x, x square, x cube, x to the power 4 kind of thing. Okay, and then we use it. Okay, if I want to use only these two, this is 2 degree. Okay, I can use these 3 degree. I can use these 4 degree. Right? What if I have two components, x1 and x2? So x1 and x2 linearity we know. Okay, this is linearity. The algorithm uses this equation to calculate your y hat. In linearity, algorithm uses this equation to calculate your y hat. In non-linearity, algorithm will use according to your degree. Okay, this is q x1 square plus x1 into x2 plus, okay, like this. Okay, that means these two components I have to transform into x1, x2, x1 square, x1 into x2, and then x2 square if I am willing to use 2 degree. All right. So let's check from sklearn dot pre-processing import polynomial features. POL is equals to what? Your polynomial features. Okay. Here what we define degree, that is equals to 2, and we define include bias, that is equals to what? False. All right. Then POL dot fit what? X. Okay. Thereafter POL dot transform X. Okay. So if you see, as I said, what are we getting? In case it is not clear, like what are we getting over here? Let me give you a basic idea over here. Let's say I'll use x1 is equals to np dot array 3 2 4 5 1 2 5 3 6 2. dot reshape 5 cross 2. Okay. Thereafter I'll do what? I can just use the same thing. Okay, and then I can use pol dot fit x1. Okay, and then pol dot transform x1. Okay, so what we got here? So if this is your actual data, okay, then this is your polynomially transformed data. Okay, that means here I have, if I consider this is x1, this is x2, okay, or let's say feature 1, this is feature 2. So I have feature 1, feature 2, feature 1 is square, feature 1 into feature 2, and then feature 2 is square, so that it can be suitably passed by the algorithm into this equation. Okay, feature 1 plus w2 into feature 2 plus w3 into feature 1 is square plus w4 into feature 1 into feature 2 plus w5 into feature 2 is square. Okay, the same thing happened when we take both the column, that is TB and radio. Okay, then let's say initially our x was what? Initially my x was 200 samples in 2 columns, but after polynomially transforming it, okay, it is what? 200 cross 5. Okay, it is what? 200 cross 5. Okay, because here also 2 is converted into what? 5 columns. So this one also is having 2 columns, that would be converted into 5 columns. Am I clear? So here for advertising data. Okay. Now after this I'll do what? It is just a copy paste, right? Like for example, we already have the polynomial features and all, so I'll separate into 2 parts, train and test. So now we are not using x, we are using polynomially transformed data. Okay. Right. Next, we'll import the algorithm and train the model. This is how we import the algorithm and train the model. Okay, so now model non-linear advertisement. Let's say for this is for multiple features. Okay, non-linear for model. Let me add over here one more thing, multiple. Okay, let's say it is for multiple feature. Done. And thereafter we'll try to do what? We'll try to evaluate it. Okay, so for evaluating, everything is fine, just take this thing. So now here the improvement happened. So when we use a single feature, that is TB, my average error was 2.54. When we use TB and radio, okay, my average error was 1.2. When I use TB with the multiple regression, TB with polynomial regression, okay, my average error was still remain 2.5. But when we use TB and radio through the polynomial regression, my error came down to 0.4. That means this is the best model that we created. It means what? It means that if I have a data, let's say TB is equals to 78.9 and radio is equals to 96.2, and I want to make the prediction of sales on it. Okay, I want to predict sales on it, right? So what I can do, I need to, if I directly feed it over here, it will not work. Okay, if I directly feed over here TV and radio, it will not work. Why it will not work? Because for the training 5 components had been used. What are those 5 components? TV, radio, a square of TV, isn't it? Thereafter, TV and radio product, which is called this is called what? Interaction. TV radio interaction. Thereafter, you have a radio. Now it will make the prediction. And this predicted value I can trust more compared to other model, because now I am getting a error value minimum, which is 0.4 average error. Okay. So if I used a polynomially transformed data for the training, I should use polynomially transformed data for the prediction as well. Am I clear? In the next session, we are going to use these things on some large scale data, almost different aspect of regression I had covered. Only Ridge and Lasso is left, but that is simple, easy to understand. Okay, we'll cover that, and thereafter we'll apply this thing on some actual data, okay, some large scale data, and we'll see how can we compare different models and how can we choose which one to be used. Is it fine?
Yes.
Yes, yes.
Okay. So let's continue with the things. We have a linear and non-linear regression that we discussed in last class, right?
Yes.
Okay. So let's have a quick visit over here. What we did. So non-linear I discussed, everything I discussed, fine. And then we build up a model. And at the end, when we build up the model using non-linearity, we get a lesser error, right? Okay, so now we will use it for our actual some larger scale, some data set like the big mat data. But before moving ahead, one more point I want to explain over here. When you use non-linearity, right? Let me just open up the file first. It is. Okay. Fine. So this is what we were working. Let me just run everything. There's a very small thing that I'll explain over here. Thereafter, we'll move for the data set.
Yes.
The big data. See, when we use non-linearity, the biggest challenge over here is what? We are transforming our data, right? That means we were given just 2 features, right? But we know if I will apply non-linearity over here, this thing is transformed into what? 5 features. If it is 2 degree, right? If it is 3 degree, then it may be more, right? So when it's like you are transforming a data from a set of 2 features to 5 features or 7 features or 10 features, because I have to use non-linearity, there may be 2 problems exist. Okay, the first problem is, see, because of 2 degree, your data size, which was actually over here having 2 features, it becomes what? Over here. Why can't I add it and you say? Okay, so here it will become 5 features, right? So 5 features means what? You are increasing the feature size. As you're increasing the feature size, what it will affect? It will affect your processing, right? That means your processing will become slower, right? Because initially model needs to use only these 2 things to train, right? As well as it needs to use only these 2 things to predict, right? Yes. But now it will use 5 different components to train and then 5 different components to predict, right? That means the processing time will be more. If you are having a small size data like advertising data we are using, we may not notice that kind of effect. But when you work on a very large scale data, real world problem, this can create a major impact. Okay, you had given a data, it is taking so much time to do the calculations and giving you the prediction. Training time will also increase, model size will increase. Suppose there is a model which is taking, suppose 10 KB of a space. Because of this thing, it may take 100 KB of a space, right? So there are so many things that happen. So how can we fix those things? Okay, to fix those things, when we are using non-linearity, right? So what we did here, I have two features called x1 and x2. To use non-linearity, we transform it into x1, x2, x1 square, x1 into x2, and then x2 square. Okay, so that it can fit into a non-linear equation, right? Like this. Okay, and it can find out x1 square plus w4 x1 into x2 plus w5 x2 square, so that it can fit into this non-linear equation and find out these coefficients. Okay, that is important. Now the point over here is only this component. Okay, this square, suppose it is 2 degree, it is a square. Suppose you are going for the 3 degree, then this equation will have some cube term as well, right? So this thing is increasing the magnitude of those magnitude of the features, the magnitude of value of the features. Okay, like initially suppose there is a feature whose value is 59. Okay, because of this thing it will become 59 into 59. Okay, that means it's like if you are using initially a 8 bit of data, okay, now you have to use 16 bit or 32 bit of data, right? So instead of we can try to check whether our model is working good or not if I will ignore these components. Okay, that means I just want to use this one. This is called what? This is called interaction term. Interaction term between multiple variables, right? So by using only interaction term also, you can do what? You can have the better model compared to a conventional or compared to a raw linear model. Okay, so what exactly I mean? Let's see. If I have over here the features, let's say this is your features and this is your label, right? So now we'll build up a model and test a model that will be a non-linear model only, but non-linear model using only interaction term. Okay, so here is the things, right? And thereafter what are we doing? We are transforming it like this. So I'll copy this thing and paste it over here. Okay, and here I'll add one more term which is called interaction only. That means one more parameter, interaction only is equals to true. So right, so if I use interaction only, then what happened? Expol. Now I will not have the square term. Okay, what am I getting? This is your TV advertisement cost, this is your radio advertisement cost, and this is the this is your product of TV and radio. All right. Okay, so it is just now we are going to use, we want that my model should use this equation to get trained. Okay, that means there will be only one more trainable parameter that would be generated, and that will be the product of these two entities. Okay, so when we were using only this much, my average error was close to 1.2 or 1.3. Okay, so let's say if I use this one, then what would be my average error? All right, so let's check. So for that we already have expol and all. I'll just I just need to split it into train and test. So I'll copy this thing. Okay, and this will I'll just this will just split it into two parts. Okay, train and test, and using this train and test we'll do what? We'll train our model Okay, I'll give it a name model multiple non-linear, let's say non-linear interaction. Okay, so I'll give it a name interaction so that later it can be easily recognized. So this is a model which I'm creating only using the interaction term. Okay, that means, yeah, obviously the features and the feature interaction. Okay, so model build up, model trained using features and feature interactions. Okay, done. So once we have a model trained, next what do? We will try to analyze its performance. So how do we analyze? We analyze like this. Okay, we make a prediction, right? We make a prediction using this model. Okay, like this, and we'll try to check the mean absolute error. So still my mean absolute error is not that much bad. Okay, it is from 1.2 or 1.3. If I use only what over here, TB and radio. Okay, my average error was close to 1.3. But if I use TB, radio, and the product of TB and radio, okay, to train my model, if I use these three things, okay, my average error is close to 0.6. That means a good sort of improvement is there, right? So whenever you build a linear model, okay, always check how is it performing with the interaction terms, right? Many case interaction term may not have a major effect, right? But in many case it can have a major effect. It can improve your model performance a lot, right? So
It'll improve if the independent variables are less. Maybe in that case the product will work more, or the opposite. When the independent variables are too many, in that case interaction only feature will work better. In what case?
correct.
With less or with more?
See, whenever we have a lesser feature, then it will work better. Okay, because if you have already suppose 10 features, 12 features, then already model is getting enough number of informations. Okay, so many information it is already getting. So in that case, interaction term may not affect much. Okay, but here we have only two components. That's why it is creating one more trainable parameters, and it is helping your model to perform more better. Done. Okay, so this is how we can make the predictions. All right, am I clear?
Yes.
Okay, so till now we had seen some different linearity, non-linearity, and everything. Now what we do, we'll move ahead and we'll try to use these kind of things into our project that we started. This one, I guess it was a Big Mart project was there, right? Where is it? I was working on Big Mart project somewhere. Just a minute. Where is it? The linear regression. This was, I guess, data science 4. B1 Panda Store. Okay, fine. Here we had used Big Mart sales data, right? So let's try to work on that. Let's try to complete that project, right? And thereafter, we'll take some more data sets to work upon. Okay, so I'll just give a quick revisit what we did actually here. So first, we accessed our data, which is a Excel data, right? In which I already told you what are the different components we have. Item identifier. These are the first few components which are representing our item, and then few components are representing our outliers. Sorry, outlets, not outliers, outlets. Okay, so we need to use these things to build a system. Okay, so these are our item. Okay, and these are our outlets. Okay. Now we did what? We just worked on these things like data type checked, we did missing value treatment, we did outliers, we treated multi-collinearity, we will check, and then skewness, right? So here data type we checked, it is all numeric data type, it is all non-numeric data type. Thereafter, these are the missing values, these are the percentage of missing values. Then we described a statistical analysis, we identified the correlation, right? And here we have the plot. Cells are what? Are right skewed. Thereafter, we start pre-processing it, right? So once we start pre-processing it, so we try to understand what is this. This is box plot. We understood what box plot is used for identifying outliers. We also understood how to analyze this one. What is this? Histogram, right? So in case of item weight, we don't have any outliers, right? Thereafter, we had seen this group by thing. How can we group based on the categorical value? This is what bivariate analysis, and analyze it. So bivariate analysis is done. Thereafter, these are the places where we have the missing values. We just find out the weights of item based on item type, right? And then based on item type, what we did, we are filling up the gaps wherever the values are missing. Okay, so this is how our missing value treated, item at missing value are treated. Thereafter, outlet size missing value, that's we are treating with the help of outlet location type. Okay, if it is tier 1, we are filling with a small. If it is tier 2, we are filling with a small. If it is tier 3, we are filling with medium. So these all things we did. For the purpose, we created a function, and the function we applied on a data column, which is used to fill the missing values. All right. Thereafter, this is done, and then here we find out the average sales value, right, of each item, and then we are just trying to do some sort of EDA, right, the exploratory data analysis kind of things. Okay, these all things I covered up over here, right? And later on we have what we did. Fine. Then we have outlets. Okay, fine. So after this, we have to build a machine learning model. Okay. So this outlet cells, as of now, I am using it as it is, and we'll try to build up a machine learning model. Right. So which machine learning model will build up over here? Build a supervised machine learning model to predict item outlet sales. Okay, so how can we build it? Let's see. I have over here item identifier in a non-numerical form. These are all non-numerical forms. So first, as per the understanding we have, algorithm required numerical value.
Numerical value. So we change it to 0, 1, 2, 3.
Right. These guys are having non-numerical value. Right. Now, whenever you have, you're right. So whenever you have a non-numerical value, we have to convert these guys into numerical form. Now, while converting these things into the numerical form, we need to understand what type of data it is. Okay, that means converting on non-numerical values into numerical forms. Okay, so for that we need what? We need to understand the type of it. Okay, obviously we'll have a categorical data that will be converted. Right, now categorical data can be nominal or can be ordinal. Okay, so ordinal means what? That means data can be ordered. Ordered means what? It's like a small, medium, large. Okay, so this is what? This one you can order, right? You can set into order. This is, like a small will come first, then medium, then large. Okay, this is what you can order. Nominal is what? A data which can't be ordered. Okay, data can't be ordered. What it means? Let's say here we have kind of a anything like say drink or yeah, right. We have a food, drink, non-consumable. Okay, consumable. So here consumable. It means what? Here you can't put it into order. Okay, you can't say that okay, food will come first, drink will come next. So we can't set any order. Or suppose there is a city name. Okay, we have multiple city name like Delhi, Lucknow, Mumbai. So you can't put those things into order, but they are categorical. Right. So the approach for the ordinal and nominal will be different. Okay, if something is ordered, right, you can do what? You do over here label encodings. I have to do the encoding, so I can do label encoding over here. Right, and something which can't be ordered, we'll use over here one hot encoding. Okay, this is important to understand. Why is it so? Let's see. If I have information like this, small, medium, large. Okay, so this can be ordered at 0, 1 and 2. So if I will, this is called label encoding. Okay, since it is already ordered, okay, and we are giving it a ordered labeling. Okay, this labeling is also ordered like 0, 1, 2. So it's like we are not manipulating the information. Okay, the information will remain as it is. It's like even after into the numerical form. Okay, non-numerical ordered, numerical also it is ordered. All right, but something which is non-ordered. Okay, like anything, like here what is your food? Okay, or let's say food, drink, non-consumable. So here if I'll give it like this 0, 1, 2. Okay, so it's like it is non-ordered, but after labeling it will get ordered. Okay, we can't, there is no kind of criteria to order it, right? But after labeling it will get ordered. So we avoid it ordering it after encoding. Okay, because this may change the information a bit internally, right? So what we do over here, we use one hot encoding. What is one hot encoding? It's like we will make it 1, 0, 0. This can be 0, 1, 0. This is 0, 0, 1. Okay, this is called one hot encoding. Okay, this will not set the value into the ordered form. All right, that means here if I will check the data, this thing is food, drink and non-consumable. So this can be one hot encoded. Here I have only two category, low fat and regular. So this can be only 0 and 1. Okay, this can be what? One hot encoding, right? Because dairy, soft drink, meat, we can't put into order. This is what? Label encoding, right? This is what? Again, this can be one hot and label both. Okay, because it can be ordered and non-ordered both. Yes. Okay, I can just use 1, 2, 3 over here. 1, 2, 3. Yeah. Right. Then we have an outlet type. Outlet type again we can use ordered and non-ordered both. Right. So, it is type 1, type 2. Yeah, right. So it's like we can do what? We can select over here which column to be one hot encoded. So one hot encoding columns. This can be your item identifier. Okay, thereafter item type. Okay, and thereafter this can be label encoding, this can be label encoding, and this can also be, we can use as a one hot encoding. For this outlet type, actually both the options are there. All right. So what we can do over here, pd dot get underscore pandas dot get dummies. So get dummies is a function, and I'll feed it this guy, which will generate the one hot encoding of these things. Okay, but it's true or false, right? So I can do what? I can use over here data type is equals to integer. Okay, so now it is better. So these three things, 0 1 0 1 1 0 like that. Then after, so first item is food, that's why this is 1, rest all are 0. This is drink, that's why 1, rest all are 0. Okay, now if I talk about these guys, these are also identified as 0 0 1 and kind of thing. Then this one, okay, first one is supermarket type 1, that's why it is 1, rest all are 0, right? So we can say this is DF 1 hot. Okay, done. Okay, now we have a DF 1 hot done. Okay, next we have over here the columns like item fat content, right? So I'll check DF item fat content. Okay, dot unique. Okay, so here I have two types of category, right? So again, for label encoding we have a library present that we can do, but that library will use alphabetical order to encode 0 and 1. Okay, so this is what I want to do next. Let's say outlet size is there. Next we have outlet location type, right? So outlet size,
Type,
and then
also outlet type.
Outlet location.
Type also medium 1, medium 2. Also outlet type.
All right. Yeah. So I can use inbuilt library, but inbuilt library will you do what? Will use kind of alphabetical order, right? So in alphabetical order, there is a possibility that suppose high I want to give over here like this. Okay, let's say I want to give this thing as 0, this is 1, this is 2, right? But there's a possibility that this guy may get 1, this guy may get 2 according to alphabetical order, right? So what we can do, we can make use of a map function. Okay, I can take this column, can use dot map. Okay, and then I can define over here.
There was another one which we can do label for that medium type and type 2. That can you scroll a little bit up?
Yeah.
You can do label encoding for the other one also. This one, yeah. Outlet type.
Label encoding. Yeah, for outlet type also we can do label encoding, but in outlet type actually there is something called grocery store, right? So grocery store should be kept like at the after all these guys or before all these guys, that is not so sure. Okay. That's why I did one hot encoding. Okay, but you can also go with, so for these kind of information actually we have both the options available. We can, because these can be considered nominal as well as ordinal. Okay, there are so many data that can be considered nominal as well as ordinal, depending upon the situation or depending upon kind of understanding, our own understanding, we use it. Or suppose if I do it nominal and then we do it ordinal and check if there is no major difference, the model performance is same, then we can go with any one of them, right?
Okay. So we can go with any one.
Okay. So now here by using map, we are doing what? We are making it 0 and 1, right? Because here you can control that which one should get 0, which one should get 1. Okay. So we have to make the changes. Here I have df1. I should use df1 only over here. But instead of df1, let me do one thing. Let me create df2. df1 I want to keep as it is for future use cases, and I will make the changes in df2. Okay. Here also df2. So here I am controlling it, that which one should get 1, which one should get 0, and then I'll update that column. Okay. Same way for the outlet size. Okay. So outlet size is having what? 3 things: small, medium, and this one. So small should get 0. Okay. Medium should get 1. Okay. And high should get what? 2. Okay. So this is called what? Label encoding. Okay. And thereafter we have the third thing. The third thing was your outlet location type. Okay. This is tier 1, tier 2, tier 3. So tier 1 I'll give just as 1. I'll not use 0 over here because already 1 is there. So I'll use 1. Okay. Tier 1 as 1. I can also use 0, but since 1 is present as tier 1, so 1 can be good over here. Just kind of removing tier from there and using 1, 2, or 3. Okay. Then I'll just run this thing. I guess it will give me fine. So now I have df2.head. So it is done, but these guys are getting null value. Why it is getting null value? The reason being this is executed for 2 times. First time when it is executed, it has given me 0, 1, and 2. But next time when I executed by mistake, right, what happened? It didn't get any kind of low fat or regular. So that's why it generated a null value. Okay, first time when I execute this line, it has given me 0, 1, and 0 and 1. But when I executed next time, it didn't get low fat and regular because low fat and regular already converted into 0 and 1. Okay, that's why it has given me a error. So what I do, I'll just run everything once. And if I run everything once, this will get corrected.
So what was the error, sir?
Okay, I'll tell you. Let it be done, then I'll explain. Where is it? It's done.
So map function is used to actually name it according to our choice. Otherwise, there is a library which we did not use. The map just gives us more control.
Right. There is a library called label encoder. Okay, if you see sklearn label encoder, okay, there is a thing through which you can here if you feed the data, okay, automatically like we have these 4 things. So you have to define first you have to import this thing, okay, then you have to define the object of it, then you have to fit the data, okay, and then when you transform, you will get the encoded value. Where is transformed use? They had used transform,
but you do not know it will give the number to which one.
Right, it will arrange it alphabetically. Okay, like Amsterdam will get 0 kind of thing, Tokyo will get alphabetically, it will generally give the things, right? Okay, but with the map, we can control which one to give in 0, 1, and 2. Okay, so now if you see here, I get 0, 1, and 2, right? So what was the problem? Initially, when I executed it, right, we got over here null value, NN, right? Okay, but now we are getting it 0, 1, 1, 0, 1 kind of thing, according to this thing. So why we got null value? It is because suppose I executed it once. Now if I will again execute it, suppose this cell I will again execute. So as this cell again I'll execute, it will do what? It will again try to map low fat into 0 and regular into 1. But we don't have any low fat over here, right? Low fat is converted already into 0. Okay, here low fat is already converted into 0 and regular is already converted into 1. Getting my point? Right? That means if I'll again execute it, it will not find low fat, it will not find regular, so it will create a null value. Understood?
Wherever it's empty.
Yeah, because when it executed for the first time, it created 0 and 1, 0 for low fat, 1 for regular. But when I execute it for second time, it is not getting low fat, not getting regular, because that is already converted, so creating null value. Here also you can see null value.
Yes,
right?
Yes. So we have a missing data, it will just put NaN.
Right. So what we do, we'll again execute it from the top. We'll click run all so that everything will get corrected.
But the NaN also will be filled.
NaN
NaN
will
be filled because that's the missing error. That's the missing error.
NaN will be filled. Like when NaN will be filled, like if you have 80%, 90% values are there, then using those 80 to 90% value, null value you can fill, right? But in this case, we like suppose in this case what happened? In this case, here I executed this, right? As I executed, low fat converted into 0, regular converted into 1. I executed it for the first time. Okay. Now when I execute it for the second time, it will again go to this column, check low fat. Okay, there is no low fat. So as there is no low fat, so it is intended to convert low fat into 0. But now it will get what? 0 over here. So it will generate null value over here. So all the value will be converted into null value. Then how can you fill it?
Okay.
Isn't it? Right? So it's like first time execution had already given me 0 and 1. If I execute it again, that means if I execute this cell for next time, okay,
it will not make sense.
Null value. Okay. So you can avoid such. I'll tell you how can you avoid such situation. To avoid such situation, transformation you can do on, here you can use df1. Okay, that means use df1 over here and update the df2.
Okay.
Getting my point? Take the information from df1. Okay, here you did what? We create a copy of df1 into df2, right? So take the information from df1, but don't change the df1 data. Okay, change the df2 data. Okay, that's how it is like if you execute it for any number of times, it will never generate a null value because you are not. This thing will not change the df1 data. This will just create what? The mapped value, and that mapped value you are updating in df2. Getting a point?
So df2 is the new column that we are creating to store these values. That df1 is the original one.
Right. df2 is a copy of df1. Okay, here we already created. Same. Okay, copy of df1 into df2. Right. So we are picking the information from df1 to map, but we are not changing the df1 data. We are keeping the df1 data as it is, like low fat, regular, whatever. Right. We are changing our df2 data. So every time it will be executed, right? Every time it will be executed, it will always get what? It will always get low fat and regular. It will never get 0 and 1. Right? So it will never give you any error. Understood?
Yes.
Okay. So now we have this thing created. Only we need to do what? Here when we have the encoded value, one encoded value, this encoded value we have to put over here. Okay, and we have to remove these guys. Okay, so how to put it? We can use over here or I can directly use like I can concat, or let me just try to use directly pd.getDummies. Directly if I will use over here, then also it will be transformed. Okay, so these values will remain as it is, they will not change. Okay, up to sales it will not change, these will not change, these will be converted. Okay, and I can use over here data type is equals to
so this get dummies means what?
dummies. Get dummies will do what? Will convert these things into the one hot encoded form. Okay, like item identifier. Item identifier is what? FD, DR or NC, right? So if you see, this will be converted into 0 and 1 and it will be arranged over here.
Got it.
Okay. So let's say over here, outlet, grocery store, supermarket, supermarket 2. So this belongs to the first sample is supermarket 1, right? So rest all are 0, only one, this one is 1. Okay. So whichever column, okay, when we use get dummies, what happened? Whichever column which is still categorical, okay, these columns will be converted into what? One hot encoded form. What is one hot encoded? It is like this: food, drink, non-consumable. So this will be one, this will represent 100, this will represent 010, this will represent 001. All right.
Right.
Okay. So first we did what? We did label encoding to the selected column. Then
So
we
it will
have
be distributed in only in 3, sir, 1 0 0, or it will be four values also, 1 0 0 0 0, or
yeah, it depends. It depends like how many categories are there. Like for example, if you see here, we have only these 3 categories, right? So it is 0 1 0. But if I talk about item type, in item type, what we have? We have so many item types: dairy, soft drink, meat. Okay, so that's why for item type you can see multiple columns are there. Okay, this is item type. Up to here we have item identifier. Now we have item type, isn't it? These all are item types. Okay, now
so like if we want to see bread, then it will be 0 1 0 0 0 0 0.
Right. Let's see. First sample is dairy product.
Yeah,
okay.
Then it's 1.
Yeah, first sample is dairy product. If you check, it is a dairy product, right? So that's why only this cell is 1, right? And rest of the cells are 0. Okay. Same way, this product, the fourth product may be fruits and vegetable. Okay, fourth product may be fruits and vegetable over here. Let me check. Oh no. Just a minute. Let it be executed. Actually, that was already dropped and again I executed, so it's generating an error. It will be done first. Taking some time for execution. It is slow, right? Okay. So see, see, fourth product is what? Fruits and vegetable, right? Isn't it? That's why you see here this fruits and vegetable is 1. Okay, so it depends like how many categories are there. If you have 10 categories, 10 columns will be created. Okay, if you have 20 categories, 20 columns will be created, right?
Yes.
Okay, so that if it is non-ordered, we are just encoding it into a kind of a 0 and 1. Like for example, I have 4 categories: A, B, C, D, E. right? So wherever A is there, that will be represented by this one. B will be represented by this one. C will be represented by this one.
Yes.
D 0 0 0 1 0 kind of thing, right? So that is called one hot encoding.
Answer. We did. Used get dummies here, but then also below you use the get dummies.
Mm-hmm.
By using get dummies, we already converted. So why
Explain
using get dummies again?
Explain. See what happened. Here I applied the get dummies only on these three columns, right? Okay, just to check what happened. Okay, right? Only these three columns. Okay, we don't have other data over here. Okay, here I did get dummies on the complete data column. Okay, so when I apply on complete data, what happened? Those columns which are already numerical, they will remain unchanged, isn't it? They are not changing at all, they remain unchanged. Okay, and the column which are categorical, they are converted into 0 and 1, right?
So at last when we are using get dummies, so it will change whether we have used label encoding or one hot encoding. So in both the cases, we will at last use get dummies. Whether we are using this one hot encoding or label encoding. In both the cases, at last to convert everything into one thing, we will use.
No. See, I'll explain. See what happened here. When I use get dummy just for explanation, what is one hot encoding? Here I used it just to explain what is one hot encoding. But when the value is generated, this value we are not updating into the data frame, right? Okay. This value we are not putting into the actual data frame. We are just leaving it here, right? Got it. When we use label encoding, okay, when we use label encoding, we updated this value into the data frame, right?
Yes, we updated it.
Okay, so as we updated this value into the data frame, these columns already becomes numerical.
Okay, already it became numerical.
So as they becomes numerical, when you use get dummies, these columns will not be affected. Get dummies will only affect the non-numerical columns like this column, or this column. Okay, get dummies will only affect what? Non-numerical column. It will not make any change in the numerical column.
Okay, it will give this 0 1 0 1 whatever it is. Yeah.
Right. So here this is done. This is just done to tell you what is one hot encoding. Okay, but for machine learning, it is not like that only these three columns will be used. For machine learning, I have to use all the columns, right? Isn't it? Other features also I have to use, isn't it? So what we did, we just take the df2 and applied get dummies. So when I apply get dummies on df2, the columns which are numerical, they remain as it is. Okay, and the column which are non-numerical, they are converted into the one hot encoded form like this. All right, like item type was non-numerical, so item type is converted into one hot encoded like this. Okay, one column for meat, one column for others, one column for seafood, one column for whatever snack foods and all. Okay, understood. These are non-numerical, they are converted into grocery store, supermarkets, they are converted into one hot encoded. So now we have a complete data, right? A data in which three columns are one hot encoded, three columns are label encoded. Like outlet size is label encoded, and others are also fat content is also label encoded. So label encoding we already did here. We did and updated the data frame, right? So I can use over df3. Okay, so I'll give you the quick revisit what we did. First, we are having a data, okay, like df1. Okay, df1. We created a copy of df1 into df2. Okay, from the df2 we selected the column for label encoding. Sorry, not from df2. We selected the column from df1. Okay, column for label encoding. Okay, right. We did the label encoding and updated the DF2 data frame. Okay, so 3 columns gets label encoding. Okay, using what? Using map function. All right, right. We
Yes,
take
yes.
the 3 columns over here from
Main column
DF1.
is 1.
Yeah, and we did label encoding and updated DF2. Now DF2 is having these 3 columns. If you see, atom fat content, label encoded, outlet size, label encoded, outlet location type, also label encoded.
Correct.
Understood? But still I have 3 columns which are non-numerical, like item identifier, item visibility, and outlet type. Okay, so these 3 columns I don't want to do label encoding, right? So we just feed it into the get dummies method, right? It will automatically pick these 3 columns only,
Right.
and leave other columns unchanged. Others remain as it is, and these 3 columns will be converted into 0 and 1, and we'll get the 1
Only the
encoded.
categorical variables will be changed to this one. Yeah.
Right.
Right.
Okay. So now we have a DF3 prepared with us. Okay. Here I update the DF3. I'm not updating DF2, and then I'll check the DF3 data types just to confirm if everything is numerical or not.
Yeah, everything is int.
Right.
64. But there's float also. Float, little bit of float.
Right. Now,
There are some.
yeah. Okay. So now what do we do? We will separate our features and labels. So what is our features? df3.drop. Okay. I want to build a model for sales prediction.
So X.
Build a model for sales value prediction. Okay. So I'll drop from here what? The sales, because sales I have to predict, right?
Yes, of course.
Where is sales item outlet? So many.
Quantity. Yeah.
Yes. Sales I have to drop from columns is equals to sales. Okay. And Y will consider only this sales column.
Item. Yeah. So we'll drop that. Yeah. Yeah. Items.
Dropping sales from X and putting it. Now we have to do what? We have to split it. So from sklearn dot model selection
Selection.
import train test split. We'll take X train, X test, Y train, and Y test. That would be equals to what? Train test split, and we'll separate X and Y from. We'll just split it. Default split ratio is what? 75%.
Yes, 75.
Then we will import sklearn dot
the
linear
algorithm.
model. Import linear regression. We'll define model A because we will try to create multiple models to compare. X train, comma Y train. Okay. Sorry.
By
Here model A
fit, model fit. Yeah.
dot fit X train, comma Y train. All right. Now we have to evaluate its performance. Okay. So for performance evaluation, what we did, we'll make the predictions on the training data first.
Correct.
Okay. And we'll store it into Y train pred. Okay. And then we'll also make the prediction on test data. Okay. So model A dot predict X test. Okay. Now we have the, for each input, okay, what do we have? We have two things. Okay. For X train I have Y train as a real value, and this is our predicted value. Okay. Same way for Y train we have, X test we have this real output, that means real sales, and this is our predicted sales.
Right.
Right. So to evaluate the error, we have to do what? Compare real sales and predicted sales, right?
Yes. Yes.
So we will import over here. Directly you can subtract and calculate absolute error, but you can also import from sklearn dot metrics import mean absolute error. Okay. This guy will do the job for you. So mean absolute error for the train data. That would be equals to what? Take the library function, feed real value and the predicted value. Okay. Mean absolute error for test data. Okay. Take it, feed it. Y test and Y test predicted. Okay. Now we will have print. We'll say what? Mean absolute error for the train will be equals to what? MAE train, right? Okay. Uh-oh. And mean absolute error for test. MA test. Okay. So I got this error. This is average error. Now the point is, how do we conclude that this is a good model or not a good model?
Correct.
Right? Because last time our average error was what?
1 point something, 1.3.
0.6, 0.68, 0.62 something, right? This time it is getting 369. This average error will totally depends upon what? The magnitude of target column.
Okay.
Right? Here. Suppose if you are building a model to predict real estate prices. Real estate prices used to be in millions.
Yes.
Right?
Yes.
So in that case, average error will be also in thousands. Right? Suppose your predicted price for a real estate property is suppose kind of a 50 million. So 50 million is predicted price. That means it is, the average, the error can be in the range of 50,000 or 100,000, right? Because when you buy a real estate property, almost sometimes 100,000 or 200,000 kind of 1 lakh or 2 lakh kind of negotiation is also there.
Yes. Yes.
Right? So in that case, the average error will also be very high. Right? So average error totally depends upon what? This particular thing, which is magnitude of target. So now if it is depend upon magnitude of target, then how do we decide that this is acceptable model, not acceptable model, good model, bad model?
Yes.
Right?
Yes.
Because there is no threshold over here. Right? That, okay, if it is we know that error value should be close to 0. Okay? But here, as much as possible, but here, error value can't be close to 0 because it is continuous value prediction, right? We can't say that the average error in the sales can be close to 0. We can't do that, right? And here we are not calculating accuracy. So if we calculate accuracy, we can say that if it is 80% accurate, 90% accurate, maximum something can be 100% accurate.
Yes.
Right? If something is 100% accurate, we say it's good. If it is 80% accurate, we can say it's fine. If it is 90% accurate, we can say it's excellent, right? But here we can't calculate accuracy. How can we calculate accuracy? Right? Because for calculating the accuracy, what we require? See, suppose, like we need categorical prediction. Okay, suppose my real value over here, okay, is true, false, true, true, false, true, like that. And the predicted value is true, false, false, true, false, false. So we can say that out of 1, 2, 3, 4, 5, 6 times, 2 times it is incorrect, right? And 4 times it is correct. So here accuracy can be calculated like this, right? Here you can calculate accuracy, but in this case accuracy we can't calculate. So what are the solutions? The solution we have is what? We will just to understand whether this model is good model, not a good model. We'll, yeah, right. We'll calculate over here R squared value. Okay, because R squared value can be in the range of R squared. It will be in the range of 0 to 1, or it may be some case negative, right? Negative is not good, but whenever it is close to 1, model will be considered as a good model. Okay, whenever R squared is close to 1, it will be considered as a good model, because R squared will not depends upon the magnitude of target. Okay, so what we calculate here? We calculate first the difference between the real value and predicted value. Okay, and the ratio of difference between real value and predicted value with respect to real value and average of real value. All right. So suppose my real value over here, and we take the sum of it. Suppose I have a real value over here 1, 2, 3, 5, 7, 6. Predicted value we are getting over here, let's say 1.2, 2.1, 3.5, 7, 8, 7, right? So what we do? We just take the average. We just have a, first we subtract like this, 1 minus 1.2, that will be 0.2, plus 2 minus this was 0.1, plus 3 minus 3.5 will be what? 0.5. Okay, 5 minus 7 is what? 2. Okay, actually you take the square of it, right? So it will be 0.2 into 0.2 will be what? 0.04, right? 224, right? 0.04. Okay, and this is 0.1 into 0.1 will be 0.01. This is 0.5 into 0.5, 0.25. Okay, here 5 minus 7 is what? Minus 2. Minus 2 square 4. Okay, thereafter 7 minus 8 is 1. This is 6 minus 7, it is 1. Okay, so this will be your numerator, right? What is denominator? We take the average of it. So what is the average of it? 1 plus 2 plus 3 plus 5 plus 7 plus 6. What is the average? Let me just have a calculate. It is 1 plus 2 plus 3 plus 5 plus 7 plus 6 divided by 6. Average is 4. Okay, the average of these guys are what? 4, right? So 1 minus 4, it is 3, right? So 3, 9 plus 2 minus 4, it is 2, 2, 2, 4, right? 3 minus 4, it is 1. 5 minus 4, it is 1. Okay, 7 minus 4, 5, 4, 5, 6, 7, 3, right? So 3 into 3, 9, plus 6 minus 4, 2, it is 4, right? Now you sum it up. What will you get? 4, 1, 5, 1, 6, 6.25, 6.26, and 0.04 will be what? 6.30. Okay, and here you will get what? 9 plus 4 is 13, right? 13 and 13, it is 26, 27, 28. Okay, so now just allow me for a minute. Okay, so now if you divide it 6.30 by 28, it means what? The difference between the real and predicted value is way lesser than the difference between the real and the average of real values. Okay, so this will come out to be small, right? If it is, it will come out to be what? 6.30 divided by 28. Okay, this is 0.225. Okay, 0.225. That means 1 minus, this is 1 minus 0.225, that will be equals to a 0. What? 775. Okay, so if we have a model we created in which the difference between predicted value and real value is very lesser than the difference between real and average of real value, that means my model is a good model, and that makes the RS squared value closer to 1, right? But in case when this difference is huge, suppose this difference is, let's say this difference comes out to be 25. So if 25 upon 28, okay, so what is 25 upon 28? Okay, this is 0.89. Okay, so RS squared value will be what? RS squared value will be close to 0.11, right? That means the model is not a good model. Okay, so whenever RS squared value closer to 0, okay, whenever it is closer to 0, that means model needs improvement. But if it is closer to 1, it will be considered as a good model. Okay. Some case it may be negative as well.
Okay.
Negative, when it will be negative, let's say my model is, I created a model which is extremely poor model, right? So in that case, this value, let's say it is 28, and suppose the difference between the real and predicted value comes out to be 38, right? So 38 upon 28 will be equals to what?
Be something one something. No, not
Yeah,
1.36.
1.36. Okay. So 1 minus 1.36 will be what? Minus 0.36, right? It will be minus.
Yes.
So when it is minus, that means it is totally unacceptable. Minus will represents a model in which the difference between real and predicted value is even more than the difference between real and average of real value.
Right.
Okay, that is a minus. Then we get RS squared minus. RS squared, if it is positive, then we can say that difference between real and predicted value, if it is positive, we can say that difference between real value and predicted value, if it is compared with real value and average of real value, compared to this guy, this is lesser. But now it depends upon like what is the strength. If it is closer to 1, as much as closer to 1, it will be considered as a good model, right? Okay, so let's try to check over here our RS squared value. For RS squared value, what we need? I need to just import over here R2 score. Okay, and then to calculate R2 score train. R2 score train will be equals to what? R2 score right, and then R2 score test. Print R2 train, R2 score train. Okay, and thereafter R2 test, R2 score test. Okay, so here it comes out to be 0.9. So whenever we have this kind of R2 score, which is close to 0.9,
Which is fine.
It is fine, but we need to go back and recheck our model. Now you say like, why we should check our model? We are getting such a high score because there is a possibility that we are using some of the features which are very highly correlated with the target. Okay, so what we do over here, we will just kind of
correlation matrix.
Yeah, we'll try to check the correlation. So df3 dot correlation.
The matrix will tell us that which are good or bad.
Yeah, so see, this is a correlation we have. Now we do what? We'll just make it SNS dot heat map. Okay, and here I do what? Annotation is equals to true. Okay, and I'll use what? Format is equals to 0.2f up to 2 decimal places, and color map I'll use what? Red, yellow, and green. Okay, so that is not very much clear, but it can be clear if I increase the figure size. PLT dot figure size is equals to, let's say, 20, and then PLT dot so. Okay, so now it is better. So now I'll see that the green. So this diagonal green is not a problem, right? We'll see those greens which are apart from the diagonal, right? So here we see a few things. Outlet age. Okay, or we'll see over here the target column. What is target column? Item
Sales.
Sales. So we'll see that is there a target column which is having a very highly correlated with anything. So this one is negatively correlated. Apart from that,
Not all
yes,
are actually, all are very less correlated. Only
here is
age.
something.
Outlet.
Here is something
Only
you can
age.
see. MRP is also good correlated, but this is a problem. Quantity sold. Okay. See, if you already know that how many quantity you will sell tomorrow, then why you need machine learning model, right? With the, if you know that I will sell 10 quantity, so you can just take a piece of paper, 10 quantity multiplied by MRP, cost price, selling price, and then it can be done, right? So quantity sold you can't use in the machine learning model if you're going to predict sales value, because sales is something that we want to predict for next week, next day. So for the next day, I can have the information about item weight. What are the items I have? Those informations are there. Item fat content I have. Item visibility I can measure, whatever the criteria I'm using for measuring. MRP I know. Identifier I know, outlet identifier, outlet age I know, outlet size I know, outlet location type I know, outlet say. This one I have to predict, but what I don't know, quantity sold. Okay, if I don't know this thing, where is it?
Yes, it's something past.
Right, if I don't know this thing, right? If I don't know this thing, then I also don't know this thing, right? Okay, so it means that quantity sold is a column that we can't use over here. Okay, that's, you know, this is why R2 score is important. With the R2 score, we actually find out that which model is it good to use or not. So what we do, we will just remove from here quantity sold as well. Like we remove this one, we also remove quantity sold. Okay, so let me take it. Okay, so quantity sold is something that can't be used, so I'll just put it here. Okay, for the machine learning model building, right? I can build a model separately to predict quantity sold, right? Okay, there can be one more model which can predict how many quantity will be sold. Now based on that, you can see error value increased, right? And you can see R2 score value comes down. Okay, but still it is positive. Okay, it means my model is having a lesser error with respect to the predicted value compared to average error, average value.
Right.
Now, can it be improved more? Yes, it can be improved more. Now we will discuss this kind of distribution. Okay, that's why for this moment I had not discussed this distribution yet. Okay, see what exactly happened in this case. I have a okay. plt.hist. Okay, let me just use it over here. plt.hist. DF of item change. See how I'll make this model work more better. Now we are working on model tuning. Histogram plot. I'll add over here one thing, plt dot ax vertical line. Okay, and where do we add? I'll add at mean value. So mean value I want to represent in a vertical line, right? And color I want to give over here, let's say green color. Okay, and I will also do what? Represent a median, and color I want to give over here was, let's say, red color. Okay. Now here is a median value and here is a mean value. Now if you see, a mean value of this guy is over here. Okay, so the number of samples lesser than the mean. Okay, how many samples we have lesser than the mean? How can you find it out? Okay, so let's say manipulating data distribution of sales. Okay, we are going to manipulate the data distribution of sales. So for that, we need to understand it first. Let's say I have a mean of sales is equals to this guy. Print mean of sales. Okay. Now what I do? I'll try to find out the number of samples lesser than mean. Okay, so this one lesser than, sorry, sales value lesser than mean of sales. Okay, so I'll get over here true or false. Okay, I'll sum it up. Okay, I get 5,000 samples. Okay, so print percentage of samples lesser than mean sales. Where percentage of sample where sales are lesser than mean sales. Okay, so I'll divide it by length of data frame. Okay, so I should use not DF over here because we are working on DF2. So let's say I'll use DF2 because from DF maybe something changed. So print. Okay, it is 58%. Okay, this is not that biased, but still. Okay, and then if I'll take over the percentage of samples more than the mean, %, yeah, 42, approximately 42. Okay, so you know here I have a data distribution which is left, which is right skewed actually, right? So with the right skewed, we had seen the performance of the model. Now I'll make a small change. Okay, what change I'll do? I will apply. I'll take this thing. Okay, and apply a log transformation on it. Okay, what I do? I'll apply a log transformation, and this log transformed value I can use over sales log. Okay, and thereafter what I do? I'll just try to plot it, the log transformed value, right? So sales log here also sales log. Okay. Okay. So now as I use this thing, it is trying to be a little bit more normally transformed. Okay, data is trying to be normal transformed. Now we'll do what? We'll build a model in which everything will remain as it is. Okay, here I'll use what? Sales log. Right. X and Y will remain as it is, only sales log, right? Thereafter, I'll take over here this splitting. Okay. And thereafter, we'll take the model preparation. Okay. And here I'll give a model B. Okay. Now this model I'll try to evaluate. So for evaluation, what we do? Again, we can make the predictions. Okay. Again, I make the predictions over here. Model B and then model B. Okay. And once we make the prediction, thereafter, we'll use over here mean absolute error. So mean absolute error is lesser, but this is what? It is lesser because the magnitude is also lesser, right? Isn't it? After the log transformation, the magnitude is lesser. That's why mean absolute error is lesser. Okay.
Yes.
Now what we do, the thing that we need to consider more is R2 scope. Okay. So here we have a R2 scope. It is what? Improved. Isn't it? So initially it was what? It was close to 0.5. Okay. What we have is 0.55. But when we use the target column as a log transform, what log transform did? Log transform convert a right skewed data into a normally distributed data, and with the normal distributed data, your model performance improved. Isn't it?
Yes.
Right. So whenever you have this kind of distribution, okay, just try to check the model performance after converting it into a thing
Into
like
log.
this. Yeah, correct. So,
Right. So we have to see many things. First, we'll use simple linear regression. Then we'll use polynomial. After that, we'll use that lograntial, where we do not use the square, we use the product. And here we'll also try to use then R square, and then we'll find that the error is more. We'll try to use the log.
right. Okay. So it means what? Let's say if I have a data, okay, and I just take any data sample from here. Okay, let's say sample number 21. Okay, and I want to make a prediction on it, right? So how can I make a prediction? We have model A dot predict. Okay, if I'll use model A dot predict, okay, so it will directly make the prediction. I only need to use two-dimensional data. So we get the predicted sales value over here, right? Okay. But at the same time, if I will take over a model B, so I'm not getting the actual sales value, right? I'm getting 7.28. Why I'm getting 7.28 from model B? Because model B was trained on what? The log transformed value of sales data, right? Model A had used actual sales data. That's why directly sales predicted. Okay. But model B had used what? The log transformed value of sales data. That's why it is not giving you the actual sales. So how can we get the actual sales? Okay, to get the actual sales, I'll tell you, see, if I have a value over here, let's say A is equals to 25. Okay, if I take the log value over here, okay, like this. Now if I, let's say this is B is the log value. Now from this log value, again I want the actual value. So what can we do? We can use over here exponential.
Inverse of log.
Exponential of B. We can use exponential of B. So again I get the actual value 24.9 and almost 25, right? Isn't it? That means to get the actual sales from the model B, after you did the prediction, you have to again do the exponential transformation over here so that you can get the actual sales.
Inverse of log. Inverse of log, right?
Yeah.
Exponential would be inverse of log, right? Inverse of log.
Right. This is inverse of log. Okay. This is inverse of log. Okay. So if you see, model B is giving me this particular sales value, model A is this one, right? But model B we can trust more because model B was having higher R squared value compared to model A. Understood?
Right.
Yeah.
Right. Right.
Okay. Right. Next. Okay, fine. Next, we want to identify how each particular model B is good, so we'll continue with the model B. How each particular information is affecting the target. So I can check the coefficient. Okay. So this is a coefficient of each value. Okay, each features. I can convert this thing into NP dot data frame. Sorry, P dot data frame. Okay. Now this is what coefficient of each component, right? So I can say what feature coefficient, right? And then feature coefficient dot index is equals to what? Your X train dot columns. Okay, whatever the columns that we can use for the training. So I can have the feature coefficient over here. All right. Now this feature coefficient I can plot to understand feature coefficient dot plot dot bar. Just to understand how each of these things are affecting. Like I can give the figure size. Is equals to, let's say width I make 16 and height I make what 8. Figure size is not working. Okay. So we got it. So it shows that item weight increasing the price, fat content is sales, as item fat content increases, the sales value decreases. Okay, so which of them are positively affecting the sales and which of them are negatively affecting the sales? Okay, grocery store is negatively affecting the sales somehow, right? Isn't it? And these guys are supermarket 1, 2, 3 are positively affecting the sales. All right. Here.
Right.
Yeah, and you can do it. One more thing that you can try. See, when we are using this thing, the training data, or let's say this particular data we are using. So, you know, the magnitude of each column is of different ranges. Like this is of, you know, like 9.30 or something like that. This is of 0 and 1. This is between 0 to 1. This is in hundreds. Okay, this is in tens, 0, 1. Okay, right? So all of them are having a different range of magnitude. Okay. So, you know,
sometimes it gives a just like you said it. If the magnitude is bigger, then the error will also be the mean value. The mean error will be also be very very big. So we can make it one. Like that.
Yeah, there are multiple effects because of this magnitude. See, first of all, the process will be slower because at the same time, a model needs to operate, right? A model needs to operate on magnitude of different, or you can say calculation will be done on data points or data values of different ranges. Okay.
And in real life, there will be like millions of rows, not like only thousands. So we have to optimize space.
Correct. So the processing will be slower. Okay, and in some algorithm, what happen if it is this magnitude will also affect the weightage. Okay, weightage means what? The coefficient that we are creating. Okay, like if there is a column which is of lesser importance, but because of higher magnitude may get a higher weightage. Right. Okay. In some of the algorithm, other thing that we have, the other problem that we may have is the error convergence. Okay, error will try to, how do error get converged? Error get converged using this pattern. Okay, it will try to find a minima, right? Yeah. So it will converge better if all of them are in the same range, that is between 0 to 1.
Normal encoding something.
Yeah, it will converge better if all the magnitudes are in the same range, all the features are in the same range between 0 to 1. Right. So this is called data normalization. Okay. So how can we do the data normalization before the training so that we can enhance the processing and we can also enhance the error optimization? So to do that, we can use min-max scaler. Okay, what is min-max scaler? Let's say I have a value 2, 3, 7, 8, 5. Okay. So to scale it, first I'll find out the minimum value. Minimum value is what? 2. Maximum value is what? 8. Okay. So I can use the formula xi minus x of minimum upon x of maximum minus x of minimum. Okay. That means this will be equals to what? 2 minus 2 upon 8 minus 2. That would be equals to 0, right? This will be 3 minus 2 upon 8 minus 2. That will be equals to 1 upon 6. That would be equals to 0.16, something like that, right? This will be what? 7 minus 2 upon 8 minus 2. This will be 5 upon 6. This will be equal to 0. Point 3, like that. This will be what? 8 minus 2 upon 8 minus 2. That will be 1. This will be 5 minus 2 upon 8 minus 2. This will be 3 upon 6. This is 0.5. Right. So in this way, if you see, the minimum will be 0, maximum will be 1, and others will remain in the range of 0 to 1. And the data pattern will remain as it is. That means the information in the data represented by what? Data pattern. So data pattern is not changing, but the magnitude reduced. Right. So this is always a good idea whenever you are building any machine learning model to do what?
To do minimum maximum.
Normalize it.
Normalizing, yeah. Normal encoding, I don't know.
Right. Normalize the features.
So it has to be done every time or?
Every time. Okay. Always you should do the normalization.
Okay.
So for the better performance and faster performance.
Whenever there are like number, 2-digit number, 3-digit number, and then float number.
Right. Like in this case, it is not required. Like for example, when we work on this thing, okay, here it is not required. Like in the advertisement data, okay, all of them are in the same range, so it is not required.
Very small data, also.
So for normalizing, what we do from sklearn dot what pre-processing import min max scalar. So scalar is equals to min max scalar, right? Then scalar dot fit x. Okay, and then we do what? Scalar dot transform x. Okay, so here if you will see xt, I'll use, right? If you see xt over here, my data gets transformed in the range of 0 to 1. All right.
Right.
Okay.
Except y.
Except yeah, y will not scale, right?
Yeah,
Because y is already getting log transform. So log transform is already scaling it, right? So here I'll split this thing. Okay, and this is done. RT score is not affected much. Okay, here I have a, this is fine. Here again I'm using x. X I will not change, right? Y is already there. It is xt and y. All right. Only y I changes. And then this is mean absolute error. This is R2. R2 is for after scaling. Here also I get R2 is for 0.72. Just a minute. Something is changed or something is not good. Okay. So this is our x and y. Here I scaled it. After scaling, it is extend. And here I am not using the log transformed, right? So without log transformed, okay, fine.
800 something. Yeah.
Okay, nah, it's fine. Okay. And here I have use the log transformed. Okay, and then I'm not updating the x because x I'm using same. Okay, here I'm using what? Xt. Okay, so here use feature xt, which is normalized data. Okay, y is as it is, and then we predict mean absolute error, this one. So this will not change obviously. Now here it is not working. Why it is not working? Because we are using normalized data. Okay, normalized data is actually already in the NumPy form. Okay, it is already a NumPy array. Okay, as it is already a NumPy array, so we don't need values. Okay, why do we use values earlier? Because earlier my data was in pandas form. So from pandas using values, we converted into NumPy matrix, and from the NumPy matrix we take the 21st row. All right. But now since it is already a NumPy matrix, after normalization, we can use directly over here. Okay. And then here also using model B. So now model A, this is model B prediction. Now you can see like why it is changed, because splitting is changed, right? Again we split it. So sample at number 21 is now different sample. This is fine. And then this is a coefficient. Now if I call the coefficient, it will give me an error. Why it will give me error? Because xtrain is now normalized data. And as xtrain is a normalized data, it is a NumPy matrix. And NumPy matrix don't have any column headers. Right? That's why I can't use columns. I can use over the x directly. Now again I'll plot it. So now it is more intuitive, you can see. Okay, here earlier MRP was having a very less coefficient value. You know, without normalization you had seen MRP was having a coefficient value very lesser. Right? Now MRP is getting the higher coefficient value, and now it is correct. Why it is correct? because if you see the correlation, right? If you see over here the correlation, the MRP is having a higher correlation with sales. This is a sales value. Okay. So if you go over here, MRP is having a, where is MRP? MRP is having a 0.57. This is a higher correlation. If it is having a higher correlation, then at the end coefficient should also be higher, right?
Yes, of course.
Isn't it? But when we were not using the normalized data, okay, when we were using the actual data, that means when we are using this actual MRP, okay, because of other things which are of different magnitude, MRP got a lesser coefficient, but now it is getting a higher coefficient after normalizing it. That means now we are getting the actual effect of each of them.
Right.
Okay, now this is more intuitive. We can see over here that for every 1.95 unit increase in MRP, sales is increasing by 1 unit.
Right.
All right.
Right.
So this is how we actually make some modifications just to get the better understanding.
So normalization we should do, and that is where it gives us the correct graph or whatever. Graph or
correct. It will give us a better intuition of each feature component that you are using for the training.
Correct.
Okay. Fine. Next, I'll tell you about the ridge regression, and I'll also tell you about the lasso. But I think before moving ahead to ridge and lasso regression, we should take a short break, right? Ridge, I was telling you, ridge, fine. Okay, so ridge and lasso, this thing actually came in picture in the year 2017 or 16 kind of thing in a research paper. Okay, so what ridge actually do, I'll show you. Okay. So for the ridge regression, okay, you need to understand this thing. What happened? Just a minute. Getting downloaded every time, huh? Okay, let's try to understand this. So what you see over here, RSS, residual sum of squared. Okay, what exactly happened? Generally, how do you calculate error? The error used to be calculated like this: y minus y hat whole square. Okay, the actual target minus predicted target square, and then you take the average of it, right? Okay, in the ridge, what happened? This thing has been modified more with one more entity, which is called, okay, here it's kind of penalizing the error more. We are penalizing it more. Okay, what are we doing? We are adding one more hyperparameter lambda. Okay, and then summation of, okay, I is equals to 1 to j or whatever, k, p, whatever you can say, or n. Okay, what is this? This is summation of weight. Okay, what is it? This is summation of weight square. Okay, now it may be a little bit confusing, right? But I'll make it clear. Okay, just have this formula with you. Okay, this is just representing the weight. Okay, now let's get back to understand this thing in detail. Okay, see here, how do we calculate error first? That we need to understand. We calculate error like this: y minus y hat whole square. That can be, error can be like this: y minus w naught minus w1 x whole square, right? Because y hat, how do we calculate? Y hat calculate like this. Is it fine? Are you getting it? What I'm writing?
Yes, sir. Yes, sir.
You see how we calculate error? Now to optimize the error, what we do? We basically calculate the gradients, right? So how do we calculate gradients? This is one, and this will be like this. This will be equals to what? Minus 2y minus y hat. This already we discussed.
Yes.
Okay, y hat into x. Okay, this is a gradient. Okay, using the gradient, what we do? We tune the values of weight. So weight naught is equals to weight naught minus, right? And weight 1 is equals to weight 1 minus. Okay, this is what we discussed. Now let's talk about the ridge part. In the ridge, what are we doing? We are penalizing the error more by using one hyperparameter and then the sum of weights. Okay, weights square. Okay, that means here it can be y minus w naught minus w1 x whole plus lambda weight naught square plus weight 1 square. All right, because we have only two weights. This is how we penalize error mode. Now point is how it will help. See, if I will now calculate the gradient, so with respect to gradient, this one will remain as it is, y minus w naught minus w1 x into minus of 1 plus what? Lambda 2 w naught. Okay, this will become 0 because we are differentiating with respect to w naught. So this will be considered as a constant and this will be 0, right? So now if you write it like this, okay, one more thing here, minus 1, if already I written minus 2, okay. So now this minus 1 will come over here, y minus y hat plus lambda 2 w naught. Now let's do it for others. This will be equals to what? 2 y minus w naught minus w1 x into minus of x plus, this is what we will differentiate. So lambda 2 w1. All right, that can be written as minus of 2 y minus y hat plus 2 lambda w1. Okay, this one also I can write like that. Two lambda w naught. Okay, so this will be our gradient. Now if this is gradient, then how it will help us in error tuning? So error will be tuned using the same formula. That means weight will be tuned using same formula. Weight is naught is equals to weight naught minus. All right, that means this will be weight naught minus y minus y hat plus 2 lambda w naught. Okay, here there will be also a learning rate, right? So here I can also use a learning rate over here. Okay, alpha is a learning rate. So this is a learning rate. Okay, so it means this will be equals to weight naught minus will plus.
Yes.
2 alpha y minus y hat, and this minus will be minus. So 2 alpha lambda w naught. Okay, and w1 will be equals to what? w1 plus 2 alpha y minus y hat into x minus 2 alpha lambda w1. Okay, so now if you here just alpha is there. Okay, so now if you compare with this guy, w naught minus what? Alpha into minus 2 y minus y hat into x, that will be equals to w naught minus plus 2 alpha y minus y hat into x. Okay, so okay, just compare this equation. W1 plus 2 alpha W1 y minus y hat into x, right? Here x will not be there. I'm sorry, here x will not be there, right? Because it is W naught, right? Okay. So if you compare these two things, what do you find? Here error is getting optimized by, sorry, weight is getting optimized by only this parameter. Okay, only this parameter is optimizing your error. Sorry, optimizing your weight. Only this parameter is optimizing your weight to optimize the error. Here we have this parameter still there. Okay? But a new entity came over here. Okay, to optimize your weight. Okay, so it is like, you know, suppose,
But it's negative.
yeah, negative, like it is just controlling the weight more. Okay, so you know, like for example, how it is effective, let's try to understand like this. Suppose if my weight value is changing and it is not changing at a pace I require, so how we regulate it? We regulate it with the help of learning rate. Okay, learning it is something we try to control the change of weights, right? We can pace up the learning or slow the learning. But you know, if we are not able to find out the optimum learning rate, okay, suppose if I'm using 0.01, it is very fast, and I'm using 0.001, it becomes very slow, right? This one is very fast, this one is very slow. I want something in between, right? So I am unable to find it out. So this particular parameter, with the help of lambda, alpha, and the weights, okay, I can control this thing and I can find out some of the learning rate or some of the speed of learning. I'll try to find out some of the speed of learning between this particular range. Optimum learning rate, which can optimize my error better. All right. Next, it will also control the overfitting. Most important thing, what it will do, it will control the overfitting. Okay, just allow me for a minute. All right, so where is it? This one. Okay, so now what I told, it will also help you in controlling the overfitting. What is overfitting? That means a model which is quite well trained on the known data. Okay, known data, it is highly accurate and giving you the very less error, right? Known data model is working extremely good, right? But unknown data, it is not working that good. So why it will run, you know, kind of a work good on, extremely good on the known data? Because of weights, right? Because of weights, because weights are only controlling the predictions, right? Okay, so by use of this ridge, we can control the change of weights, or we can control the magnitude of weights, okay, in a way that overfitting can also be controlled. All right, it just add one more parameter to control your weights more. All right, okay, so let's try to check how is it working. So for using it, okay, I'll do what from sklearn dot linear model import ridge regression. Okay. Now I'll use model C is equals to ridge regression. Uh-oh. Okay. Then model C dot fit extend comma y train.
So wherever we can apply linear regression, we can apply lasso and ridge also.
I can apply Lasso and ridge also, but here I am getting an error.
Error.
Just a minute, I'm maybe missing some parameter over here. I'm missing this alpha value actually. Okay. Alpha is what? Alpha is this thing. Here alpha is actually shown. Alpha is used for the learning rate, right? But here alpha is used for this guy. All right. So for learning rate, you can use lambda, isn't it? Learning rate, you can make it lambda, and this one you can consider as alpha. Okay, because here this one is in the library. Alpha is you because here this one. Okay. May not be, here this one is considered as alpha in the library, right? So alpha lambda is just a notation, right? Okay, so you can consider this thing as alpha, it's fine, nothing to worry. So it is just a notation. Okay, so when I am using it, it is expecting to give the alpha value. So let's give the alpha value over here. Okay, 1. Okay, and with the alpha value 1, what happened? Why it is giving an error? Model says equals to. Okay, only have to give, I guess, ridge, right? I don't have to give ridge regression, just ridge. Now is it working? I guess it is working. Am I correct or not? Linear is for value and then fitting it. Okay. Ridge classifier. I want ridge regression rate. Skill under model. It's okay. Ridge regression, fine. Okay. So now it is done. Okay. What I do? I'll try to evaluate the performance. Okay. Performance I don't think will change much. But what will change, I'll show you. There is something that will change.
Error will change, I guess.
No, error will remain almost same. Okay. But first I have to make the prediction. So for the prediction, I'll take this thing and paste. Okay. So I will use model C now. Okay. Model C not predict extend in this one. Mean absolute error almost remain same. Earlier mean absolute error was 0.42, almost same, right? R2 score value almost remain same. This will not change much. Okay, you can do what? You can tune it to see the effect. Let's say it is 1.0, you can make it 0.1. Okay, and you can check. Okay, you can use over 0.01. Okay. Okay, if you want to be more aggressive, you can make it 10. Okay, this is something that you can control, that you can change. Okay, but as of now, let's make it 1 only. Okay, I'll tell you the next thing that is called GridSearchCV. So through GridSearchCV, you can better optimize the hyperparameter. I'll tell you that later on, but as of now, let it be 1. Now what I do, I will calculate this thing that is a coefficient. Okay, feature coefficient using model C, feature coefficient using ridge. Okay, feature coefficient ridge. Okay. And then I'll try to plot it. Okay. So feature coefficient using RIS. Anything change? 0.02 or something I have over here. 0. Minus 0.02, 0.01, minus 0.03, 1.95. Anything changed? It is almost same. Nothing is changed. Okay. If I use 0.1, zero point zero 0.01 minus 0.03, is it change? I guess this guy is not making any change. Almost things remain same. All right. So with the reach, we are not getting any change over here because this is already a good model, and here we don't have overfitting. So since we don't have overfitting, we'll not find any major change over here. Now I'll use Lasso. Okay, in the Lasso, we'll see a difference. Okay, what happened in Lasso exactly? In case of Lasso, what change happened? First of all, to understand this, you need to check the formula of Lasso. In the Lasso, here, the same thing happened, but we don't use a square. Here, what we use? The mode. Okay, the mode of it. Right? What it means? See, here we had used a square term, right? Okay. So as we use a square term, because of this square, this 2 came. Right? Because this is a square term, that's why when you differentiate, this square 2 came over here and then did, right? In Lasso, we don't use a square term. It is just error is equals to y minus y hat plus summation of I is equal to 0 to n lambda, and it is
Just the weight.
just the absolute value of weights. Okay, that means it is y minus w0 minus w1 x whole square plus lambda w0 plus w1, like this, right? So when you differentiate, that square term will not come over. That means 2 will not be there, right? That is a difference. Okay. So if I will implement the Lasso over here, I'll just copy and paste the thing quickly. It will not take much time. Okay. Lasso. Okay. And I'm using alpha same. Let's say it is D. Okay. And thereafter, I'll make the predictions. Okay, and thereafter I'll make the evaluate the error. Mean absolute error will everything will not. Oh, sorry, it should be D, right? See, model D. Okay, so now this is your average error. This is almost same. Okay, and thereafter we have the R2 score. R2 score came down over here, right? Isn't it? R2 score is affected over here. Let me change the alpha, make it 1. Now it is more negative. Okay, so here this thing is affected. Okay, let us use 0.01. Now it is more better. Okay, 0.01 it is better. So you can see Lasso is something which is actually creating a difference, but with 0.01 we are getting the same level of things. Okay, now what I do, I'll try to find out model D dot coefficient. So when you find out the coefficient, you can see a lot of coefficients become 0, right? Okay, so what Lasso actually do? Lasso will, if you are using Lasso, it will help you in identifying the most important features. Okay, those features which are not important, or it is just very less important. Res or normal regression will still give you a very small coefficient like this 0.001 or something like that, right? Okay, that means these coefficients are extremely small, close to zero. But Lasso is very aggressive. What it do? It will just remove these things, just make these things zero. Okay,
Right.
and only these guys which are important will get some of the coefficient.
But it
Okay.
is minus. It's coming minus also.
It is coming minus. Oh, no need to worry about the minus. It is just zero because this one was having the negative 0.02, right?
But
So
sir, but this I know this is not valuable. You can scroll up a little bit.
mhm.
Yeah, the up the values were the values were.
Where this one?
Yeah, exactly. So here, see this. This is also very small item type household. The
Correct.
population is very less, so this will not be zero. Or
No. Which one? Which
from
one?
see this item type household is 0.000, so it has no significance. This
Item type household. This one 0.007. Okay.
yeah,
So
even
item type.
this
So let's see which of them are actually zero. What I do, I'll just convert this thing into data frame first. Okay. And I'll make it what? Lasso coefficient. Okay. And then I'll make Lasso coefficient dot index is equals to x dot columns, right? So Lasso coefficient. Okay. So it becomes zero, you can see, isn't it?
yes.
So here the thing is, it just make whatever column which are of very less importance. Okay, like here all of them got some of the coefficient. Okay, but Lasso is doing what? It will just pick up the most important columns. Okay, those columns which are of very less importance will get automatically the coefficient zero, right?
Or
And
minus only.
that
Or minus.
minus 0 0 same thing, right?
Yeah.
Okay,
So only
so
it says. Yeah. Only it's.
so it says that for your sales value prediction,
MRP.
actually you required only these 4 columns or 5 columns,
MRP. Yeah. MRP
right?
and the grocery store is negatively correlated, right? Outlet
Hmm.
because it's down. It's
Right.
yeah, right.
Yeah. So it means from the data, from this whole data, even if I will use only these things, like this is your actual data, right? Okay. Now from this data, if I will pick only these 4 columns, okay, which are the columns like item MRP,
MRP and
okay, and sorry, item MRP, okay. And thereafter I'll take these guys, okay, and
sir,
using
how is it negatively correlated with outlet type grocery store? Why is it not positively correlated?
maybe like in the grocery store sales values are like whenever the grocery store value is 1, okay, sales values are comparatively lower than when the supermarket or supermarket 1 2, like whenever these values are 1, okay, whenever these values are compared to that condition, whenever the grocery store is 1, sales value may be lower. Okay,
Maybe
that's why it is saying it identified that whenever the grocery store is 1, the sales values are decreasing. Okay, so if I will use it x new, okay, so Lasso regression is very interesting algorithm which helps us in doing the feature selection, isn't it?
right.
Okay, so y new is equals to what? Y new is equals to y, right? Now if I build up a model using this thing, right, let's say xtrain underscore new is equals to xtrain new comma xtest underscore new comma ytest underscore new ytrain underscore new comma ytest underscore new. Okay, this will be equals to what? Train test split. Okay, x new comma y underscore new. Okay, and thereafter I can define model E is equals to Lasso, where alpha can be equals to what? 0.01, right? And model E dot fit what? This xtrain new. I'm not using over here normalization, right? Without normalization, all right?
Yeah.
And thereafter I fit it, and thereafter I'll make a prediction. So ypred underscore new is ypred train. Ypred train underscore new is equals to model E dot predict. Okay, xtrain new. Okay, and thereafter ypred test xtest new. Okay, and thereafter we'll try to evaluate the performance. So for the performance we required what? Mean absolute error. Mean absolute error will be what? Mean absolute error, and then compare ytrain underscore new comma the predicted value on this thing. Okay, and thereafter mean absolute error on the train and mean absolute error on test. Okay, this is ytrain, this is ytest. Ytest new. Okay. And then predicted value on ytest. Okay, so this is your mean absolute error. Now we can have the mean R2 score value. R2 score. Okay, and then R2 score. Okay, another. Okay, this is coming same almost, right? Okay, fine. So what we had seen over here in this discussion, that we can optimize the error, okay, with the help of some of the modification in the distribution of target column. If target column is right skewed, we can do what? We can make it normally transformed, and then we can make the performance better, right? Apart from that, we can also work on the feature selection, right? So now we have a model which is using only 5 features, okay, 5 features to get trained. So this will be considered as a better model, isn't it? Because it is a lightweight, it requires only 5 features. It don't require all the information that is present over here in the data, right? So we need not to accumulate all these informations, okay, to predict something. Now my model is lightweight, it can predict at the same level of accuracy, okay, at the same level of accuracy, at the same level of error, even with a lesser number of features. Okay, so we can So when you build up the machine learning model, it is not just about optimizing the error. It is also about the feature selection, okay, and optimizing the resource.
Right.
Clear?
And sir, we Lasso, I understood that it is used for feature selection. The most important features we can use, and then it will give almost a similar score, like normalization and all. But what will be the exact difference between that ridge? Ridge. Why do we why using ridge?
Okay. So ridge over here is not having any specific role. That it is not playing any specific role over here, because ridge is used when we get a overfit model, like when I'll work on some other example, okay, and we get some overfit model, okay. So in that case ridge can play important role, okay. In these kind of cases you don't find major change in the ridge, almost you are getting the same kind of over here. If I see models, if I will check over here, I'll get the same level over here, right? And
there's not
everything is same, and the coefficient is also almost same. Coefficient is also not changing.
Yeah.
0.96, 0.21. It is also, it is also not changing, right?
Right.
So here you will not see a major difference, but you should know it. You will find, I'll show you the effect of ridge when we work on some of the data where the features are too much, like we are working with a large set of features, okay, and all the features are important, right, and we get some overfit kind of a situation, right. In that case ridge will play important, like mostly it will play important role when we work on neural network, okay. In normal regression you will not find such a major effect of ridge, okay. It will it seems to be same. We think that okay, ridge is almost same than linear, okay. But in neural network, what happened, we create neurons. Because of the neurons, multi-layer neurons, we will work with so many weights, okay. Like in neural network we will not have 10, 20, 30, 40 weights. We'll have the thousands of weights, okay. And because of thousands of weights, what happened, model gets a lot of time overfit,
Okay.
right. And in that case, that overfitting get controlled a lot by the ridge. Ridge is majorly used for controlling the overfitting. Here, if the model is not overfit, that's why we don't find any major effect of it. Okay, but just keep in mind, I'll give you some of the example where this will be very important. As of now, for this case, Lasso is good.
Fine. And sir, we saw that MRP affects it, and also the grocery store type. So I just still did not understand why grocery store type is the important one, but it is negatively correlated. The grocery store type is just the size, right? I think the size is bigger, smaller. Where you have bigger size, the store is bigger, then the sales will be more, right? So this outlet type.
It may be in the data, like what the data that we are using in the data, maybe whenever the grocery store is true, the sales is comparatively lower, okay, compared to supermarket one, it may be lower, okay. So that's why it is identifying it as a negatively correlated.
Maybe size, right?
Size, grocery store is actually not size over here, because size is represented by small, medium, and large.
Something else. Okay. Grocery store means it has negative correlated. That means
whenever the grocery store value is high, that means whenever there is a grocery store in the data, okay. So sales value in those cases comparatively lower compared to supermarket 1 to 3, it is lower. That's why it identified it as a negatively correlated.
Okay.
Like it just compared a few things, right?
Right.
But one more thing that I want to check here, auto score value came down a bit. Oh, no, it's fine, because it is splitting every time. Random split is there, so that's why. Okay, you can fix it by using over here random state.
Yeah, then it, yes. If you do this in everything, then the training and test will be the same value we will get.
Right, correct.
Then it will not change. It will not shuffle.
Correct. Okay, this is called there is a concept over here which is called cross validation. Okay, so what is cross validation? That is again a thing of validating the model. So cross validation is actually just validating your model on different
0, 1, 4 quadrants, I guess, right?
Yeah, on different sets of data. Okay. See, when we split, every time we split gives us random data, right? Okay. So cross validation will do what? Cross validation will split it like it is a 5-fold cross validation. That means your data will be splitted for 5 times. Okay. And every time the training and test data will be different. All right. And then when every time the training and test data will be different, every time the model performance will be different.
Yes.
Okay. Then we take the average of all the performance. Okay. To finally, like for example, here what we do from sklearn dot what model selection import cross validation score. Okay, so you can check it over here. Cross validation in the scikit-learn, how to use it. Okay, so here it is normal, and here it is just like when you change the random state from 0 to 1 to 3, every time the data in train and test will be different. Okay, for random state 0 we have different train and test, for random state 1 we have different train and test, for random state 2 we have different train and test, right? So what do we do over here? We can use this cross validation. Okay, so in this cross validation we can use it like this. From sklearn.model score import cross validation score, that already we imported. Next, what it is saying, we have to define the model, right? So let's say I'll define a model over here. Model f is equals to this one. Okay, like this we will define a model, svm.svc, same way define a model, and thereafter I require cross validation score. So I'll just get it from here and paste it over here. Okay, so here I'll feed the model f. Okay, and then we have x and y. Okay, we can just use x and y, and that's fine. But x is not a normalized data, right? X is not a normalized data. What is normalized data? I'm planning to use normalized data, right? So where we normalized it? What is normalized data? X train, y sales. Where is normalizing? XT is normalized data, right? XT is our normalized data. Where is XT? Where we normalized it? Here we normalized it, right? So XT is our normalized. So let's try with XT. Okay. So now if I print the scores, okay, I get 5 scores over here. This is a test score, right? This shows that my R2 score value will be in the range of 0.70 to 0.73. Okay, it can be, let's say I can go for 10 cross validation, right? So, and the average score will be what? Average cross validation score will be equals to what? NP dot mean of scores. Okay, that is close to 0.71, and actually also 0. Close to 71 to 0.72, right? So it is just help us in identifying, like suppose here I done it, okay, and here I got the best information in the train and test. Okay, so when I got the best information in the train and test, we get a very good accuracy. But may possible, okay, some of the information, my model actual performance may be up to not that particular mark. Actual performance may be lower, right? So what we do, we just split it for 10 different times, and every time we train it, and then this is the average score of our test data after every split. Okay, so the average score of test data after every split is 0.71. That means we can assume that R2 score value will be close to 0.71, and most of the time it will be above 0.7. Okay, only one time it is very less, but most of the time it is above 0.7. Okay. Then there is called GridSearchCV. What is GridSearchCV? See, when we have to decide a hyperparameter like this, okay, many a time it's difficult to decide the hyperparameter. So what we do, we use grid search cross validation CV, or we can also use random search CV. Okay, these are two important things. Okay, that means suppose here I have only one hyperparameter. As I have only one hyperparameter, I can change. I can go for hit and try. I can check one. I can check two. Like for example, let's say I'll make it one. Okay, I'll make it one. I get a poor score. I can make it 0.1. I get again a poor score. Okay, I can make it 0.01. Okay, it's better. Okay, I can make it 0.05. Okay, it's lesser. Right, I can make it 0.001. It is again better. I can make it 0.005. So it is, that's how I can go for hit and try, because I have only one. But suppose if I have so many hyperparameters, okay, so going for hit and trial will not be possible. Okay, that we'll see in upcoming algorithms. We have 3 parameters, 4 parameters. Like suppose if I have let's say 3 hyperparameters, okay, like hyperparameter 1, hyperparameter, like this. I have 3 hyperparameter A, B, and C, right? So actually, you can do what? You have to tune all these 3 values. Okay, so suppose for A you want to check 0.1, 0.01. This is 0.001. Okay, for B you want to check, let's say 1, 2, 3. Okay, for C, let's say you want to check 10, 20, and 30. Okay, now how many combinations are possible? Okay, there are a lot of combinations are possible if you're using 3 hyperparameters. The first combination can be what? 0.1, 1, 10. Second combination can be what? 0.1, 1, 20. Third combination is what? 0.1, 1, 30. Then 0.1, 2, 10. Then 0.1, 2, 20. Right? Then 0.1, 2, 30. Right? So it would be like 3 cross 3 cross 3, like, a lot of combinations are possible, right? Right? So manually testing each combination will be very difficult. So we'll make use of GridSearchCV that will test your all the combinations on multiple cross validations. Okay. Here I can define like this. First, you can define the parameter grid. Okay. Parameter grid here we define like this. Parameter grid is equals to what? I have to define according to our algorithm. So for us it is alpha, right? Just a minute. Yes. Okay. So for us it is our alpha. So I'll define over here alpha is equals to, let's say 1. Sorry, let's say 10, 1, 0.1, 0.01, 0.001, and 0.0001. Okay. I want my model to test all these parameters. right? So here it should be colon. Okay. So first I define the parameter grid. Once I define the parameter grid like this, okay, like this, okay. Thereafter we have to use these things like define the model. Grid model is equals to. I have to also import over here from sklearn dot model selection import GridSearchCV. Okay, so GridSearchCV. Okay, here I have to define few things. First, I have to define estimator. So, what is your estimator? Let's say model F, or let's say I have to define a new model. Let me define a new model. Okay. Let's say I'll define a new model over model G, for which I don't know. So first I will define our estimator. Let's say model G. Okay, first is estimator. Second thing I would define is what is a parameter grid. That is already we defined param underscore grid. Okay, and third thing I want over here cross validation. Okay, so CV is equals to, let's say 5 cross validation I want. Okay, now I'll do what? I'll fit the data in this grid model. Grid model dot fit what? This thing. Okay. Now I can identify the best hyperparameter. So grid model dot best estimator. Sorry, best params. Okay, and grid model dot best score. Best score. Okay, and thereafter I can have the best model. I can also pick from here. Best model is equals to what? Grid model dot best estimator, right? So now I have the best model also identified, and this best model I can use for the prediction further. So it is saying the best alpha is 10 to the power. This one it is picking up. Okay, this one is what 10 to the power minus 5. Okay, if I don't give it, okay, then it will take other one. Okay, like this. This one it is identifying as the best one. Okay, out of all these, right? So this is how we can do it. But you know, many a time if we have a lot of hyperparameter, grid search becomes very slow, right? Suppose if you are working with 10 hyperparameters, and for every hyperparameter you have 5 combinations, so it will become very difficult to identify. So in those cases, what we do, we go for random search. Okay, that means don't go for each combination. Okay, just randomly search for one of them. Okay, and do it, right? So random grid model. Everything is same. Only grid search will check each possible combination. Random will not check each combination. It will just take randomly.
So out of 10, 1, 0.1, 0.01, 0.001, it will just pick anything.
Yeah, right. It will pick few of them and try to. Here it will pick. Actually, we have only 4 or 5 options are there. So here it may take all of them. But if we have more options, it will pick any one of them. Like only few of them. So random search and grid search is same over here. Okay, I am telling you over here as a very basic understanding. Later on, when we work on some more advanced algorithm in which more hyperparameters are there, then you see the difference between a grid search and random search. It's just the processing time. Grid search will try each and every combination, so it is little slow. Random search will randomly try few of the combinations, so it is faster. Okay. So what we had seen, how can we test on different splits and can give a kind of an average of accuracy, average of error we can calculate through cross validation. In case if hyperparameter we can't find easily, we can go for grid search, give a range of hyperparameter, and from that range it will give you the best hyperparameter. All right.
So in this alpha, can we write beta, or is just alpha only? That's the format.
It is alpha we have to give. Why we have to give alpha? Because we are using Lasso, right? And if you check the Lasso thing, okay, in the Lasso this parameter is defined by alpha. It is alpha recognizing the parameter. That's why we're using alpha, right? If you give lambda or beta or something else, the inbuilt method will not identify what you want to define. All right.
Okay.
That is why we are giving alpha. Understood?
Yes. Yes, sir.
Okay, so these are the things we discussed for today. Again, these will be again repeated. As of now, we have used it at a very basic level. Okay, these are going to be covered in more detail or more deeper examples we will take with some more different case studies, right? Tomorrow I am planning to start your classification thing. Okay, and thereafter we'll work on some of the capstone project. All right. Is it enough for today?
Yes, sir. Actually, we extended the class. We extended the class by half an hour.
Is it?
Yeah. So right now it's what? Almost 120. 120.
Oh. I have not noticed.
Okay.
I have not noticed. Okay, so where are you having some work to do?